The water here is deeper, cooler, and far less forgiving than the shallow flats of the previous world. Light still penetrates, but it arrives fractured and unstable, broken into shifting bands by the surface above. The seafloor is a patchwork of sand, rubble, and scattered algae, interrupted by low coral outcrops that cast soft shadows across the terrain. It is an environment defined by constant motion, not of bodies, but of light itself. Patterns ripple across every surface, moving in silent waves that distort outlines and dissolve edges. In this restless visual field, clarity is a rare commodity, and anything that can control how it is seen gains a decisive advantage. A cuttlefish drifts just above the substrate, its body angled slightly forward, fins undulating in a continuous, almost effortless rhythm. Unlike the octopus, it does not crawl or cling. It hovers, suspended between water and ground, a predator that moves with the same fluid instability as the light around it. At first glance, it appears unremarkable, its coloration matching the sandy tones beneath it, its outline softened by subtle gradients that blur the boundary between animal and environment. But this stillness is deceptive. Beneath the surface of its skin, a far more complex system is already in motion. The cuttlefish possesses one of the most sophisticated visual display systems in the natural world, built from layers of specialized cells that interact to produce rapid, high-resolution changes in appearance. The outermost layer contains chromatophores, tiny sacs of pigment surrounded by radial muscles. When these muscles contract, the sacs expand, revealing colors ranging from deep browns and blacks to yellows and reds. Beneath them lie iridophores, structures that reflect light in specific wavelengths, creating iridescent blues, greens, and metallic sheens. Deeper still are leucophores, which scatter ambient light and contribute to brightness and contrast. Together, these layers form a dynamic canvas, one that can be rewritten in fractions of a second. Yet the true power of this system is not in its ability to change color alone. It is the integration of color, pattern, and texture into a single coordinated display. As the cuttlefish hovers, its skin begins to shift, not randomly, but in patterns that mirror the environment with astonishing precision. Patches of dark pigment expand and contract, aligning with the shadows cast by nearby rocks. Lighter areas adjust to match the reflective qualities of the sand. Small protrusions on the skin, known as papillae, rise and fall, altering the animal's texture to mimic the roughness of coral or the smoothness of sediment. The result is not just a visual match, but a structural one, an illusion that operates across multiple sensory channels. This form of camouflage is often described as dynamic, but the term barely captures its complexity. The cuttlefish is not simply blending into a static background. It is responding to a constantly changing visual environment, recalibrating its appearance in real time as light shifts and perspectives change. Its eyes, large and highly developed, scan the surroundings with remarkable acuity, detecting not only color and brightness, but also polarization of light, a feature invisible to most predators. This additional layer of perception allows the cuttlefish to extract information about surfaces and objects that would otherwise remain hidden, refining its camouflage to a level that approaches predictive accuracy. As it moves, the illusion moves with it. The patterns on its skin do not remain fixed, but flow across its body in coordination with its motion, maintaining the integrity of the disguise even as the animal changes position. This is a critical distinction. Static camouflage is effective only when the animal remains still. Movement typically breaks the illusion, drawing attention and revealing the underlying form. The cuttlefish avoids this limitation by integrating motion into the camouflage itself. Its skin becomes a moving extension of the environment, allowing it to travel without announcing its presence. But camouflage is only one aspect of its strategy. The same system that allows the cuttlefish to disappear can also be used to create some of the most conspicuous displays in the ocean. And it is in this transition, from invisibility to visibility, that the animal reveals a second, more aggressive application of its abilities. A small fish moves cautiously along the edge of a coral fragment, its body angled downward as it searches for food among the sand. It is alert, but not alarmed. The environment here is familiar, and while danger is always present, it is also diffuse, spread across many potential sources, rather than concentrated in a single, obvious threat. The cuttlefish approaches slowly, maintaining a distance that keeps it outside the fish's immediate awareness. Its body remains low, its coloration subdued, blending seamlessly with the background. Then, without warning, the surface of the cuttlefish erupts into motion. Bands of contrasting color begin to pulse across its body, moving in rapid rhythmic waves from head to tail. Dark and light stripes alternate in quick succession, creating a flickering effect that disrupts the visual field of the prey. This display is not random. It is highly structured, with precise timing and spacing that generate a phenomenon known as motion dazzle. The fish, which relies on detecting coherent movement to identify threats, is suddenly confronted with a pattern that overwhelms its visual processing. The direction and speed of the cuttlefish become difficult to interpret, its outline dissolving into a cascade of shifting contrasts. At the same time, the cuttlefish adjusts its posture, extending its arms slightly forward, preparing for the final phase of the attack. The pulsing intensifies, the waves of color accelerating, creating a hypnotic effect that appears to hold the fish in place. Whether this is a true neurological disruption or a behavioral hesitation triggered by sensory overload remains a subject of study. But the outcome is clear. The prey does not flee. In a fraction of a second, the cuttlefish strikes. Its two specialized feeding tentacles shoot forward with remarkable speed, extending far beyond the length of its body. The tips, equipped with adhesive pads, make contact with the fish, securing it before it can react. The tentacles retract just as quickly, pulling the prey toward the cuttlefish's beak, where it is subdued and consumed. The entire sequence, from the initiation of the display to the capture of the prey, unfolds in less time than it takes for the surrounding light patterns to shift. This use of visual display as a hunting tool represents a different dimension of illusion. Here, the cuttlefish is not trying to hide or to resemble another organism. It is actively manipulating the sensory experience of its prey, creating conditions that reduce the likelihood of escape. The flashing patterns are not simply signals. They are weapons, designed to interfere with perception and decision-making. The effectiveness of this strategy depends on the integration of multiple systems. The cuttlefish must detect the presence and position of its prey, assess the appropriate distance for initiating the display, and coordinate the timing of its attack with the peak of the visual disruption. Its nervous system, highly centralized compared to many other invertebrates, allows for rapid processing and precise control of these actions. Each chromatophore is innervated directly, enabling fine-scale adjustments across the skin, while the muscles controlling the tentacles operate with a speed and alcohol that rival those of many vertebrate predators. Beyond hunting, the cuttlefish uses its skin displays in social interactions, adding yet another layer of complexity to its visual repertoire. When encountering other members of its species, it can produce patterns that convey information about identity, reproductive status, and dominance. In some cases, individuals have been observed displaying different patterns on opposite sides of their bodies simultaneously, signaling to a potential mate on one side while presenting a more neutral or even deceptive appearance to a rival on the other. This ability to partition its display suggests a level of control that extends beyond simple pattern generation into the realm of targeted communication. The ecological implications of these abilities are significant. In an environment where visibility is both a risk and a resource, the cuttlefish occupies a unique position. It can withdraw from detection when necessary, reducing its exposure to predators, but it can also project highly visible signals when the situation demands it, whether for hunting or social interaction. This flexibility allows it to navigate a wide range of contexts, adapting its strategy to the immediate conditions of its surroundings. As the day progresses, the angle of the sun changes, altering the quality of light that reaches the sea floor. Shadows lengthen, contrasts deepen, and the patterns that once provided effective camouflage may no longer align perfectly with the environment. The cuttlefish responds accordingly, its skin shifting once more, recalibrating to the new visual conditions. This continuous adjustment underscores a fundamental aspect of its biology. It is not operating with a fixed set of appearances, but with a system that is constantly updated based on incoming information. In the broader context of evolution, the cuttlefish represents an extreme example of how sensory and motor systems can co-evolve to produce highly specialized behaviors. Its visual perception informs its skin displays, which in turn influence the behavior of other organisms, creating feedback loops that shape interactions at multiple levels. Predators that rely on vision must contend with an animal that can alter its appearance in real time, while prey species must navigate an environment where signals can no longer be taken at face value. As evening approaches and the light begins to fade, the cuttlefish descends closer to the substrate, its movements slowing, its displays becoming less pronounced. The need for active hunting diminishes as visibility decreases, and the risks associated with conspicuous signaling increase. It settles into a more subdued state, its skin adopting patterns that blend with the darkening sea floor, its body becoming once again a part of the background. In this transition, the full spectrum of its abilities becomes clear. The cuttlefish is not defined by a single strategy, but by the capacity to shift between strategies as conditions change. It can be invisible or intensely visible, passive or aggressive, deceptive or communicative. Its skin is not merely a covering, but an interface between its internal state and the external world, a medium through which it negotiates the challenges of survival. In a habitat where light is both a guide and a hazard, where perception determines outcome, the cuttlefish does not simply exist within the visual landscape. It controls it. Through instantaneous skin illusion, it reshapes how it is seen, how others respond, and ultimately, how it lives. The reef at mid-depth is a place of structure and interruption, where the seafloor is no longer a flat expanse, but a complex architecture of ridges, crevices, overhangs, and broken coral skeletons layered over one another. Light still reaches this world, but it arrives fractured, filtered through water, thick with suspended particles and shifting currents. Shadows are everywhere, but none of them are stable. They stretch, contract, and dissolve as waves pass above, turning the entire environment into a constantly changing puzzle of contrast and texture. In such a landscape, survival does not depend on speed alone or strength alone, but on the ability to interpret chaos and become part of it so completely that even a searching eye cannot separate organism from environment. An octopus emerges slowly from the narrow entrance of a rocky crevice, its body flowing outward as if poured rather than pushed. There is no rigid frame, no skeletal structure to define its shape. Instead, it exists as a controlled mass of muscle and nerve, capable of reconfiguring itself in ways that seem to defy the usual constraints of anatomy. At first, it appears dark, its skin mottled in shades of brown and grey that echo the surrounding rock. But this initial impression is only a starting point, a baseline from which far more precise adjustments begin to unfold. The octopus does not simply match the color of its surroundings. It studies them. Its eyes, positioned high on its head, scan the immediate environment, capturing information about light intensity, direction, and the distribution of textures across surfaces. Unlike many animals that rely on fixed patterns or limited color ranges, the octopus processes this visual input and translates it directly into changes across its skin. Chromatophores expand and contract in coordinated waves, adjusting hue and contrast, while deeper layers reflect and scatter light to fine-tune brightness. Yet what truly defines its camouflage is not color alone, but structure. Across its skin, small muscular projections begin to rise. These are papillae, flexible extensions that can be inflated or flattened at will, transforming the surface of the octopus from smooth to rough, from featureless to intricately textured. As it moves onto a patch of broken coral, the papillae extend unevenly, creating a jagged outline that mirrors the irregular shapes of the substrate. The body no longer appears as a single, continuous form. It becomes a collection of fragments, each one blending into the visual noise of the reef. This is camouflage not as concealment, but as disassembly. The octopus does not hide by becoming invisible. It hides by breaking its identity into pieces that the observer's brain cannot easily reassemble. predators searching for recognizable shapes. Curves that suggest a body, symmetry that indicates an organism, find only a scatter of textures that match the background too closely to stand out. The octopus remains in full view, yet unrecognized. As it moves, this illusion must be maintained. Movement is the great betrayer of camouflage, the moment when even the best disguise can collapse under the simple fact of displacement. But the octopus approaches motion differently. It does not glide smoothly across the reef like a fish, nor does it dart in sudden bursts. Instead, it advances in small, deliberate increments, each movement carefully aligned with the shifting patterns of light and shadow around it. When a wave passes overhead and the shadows ripple, the octopus moves with them, synchronizing its motion with the environment's own instability. In doing so, it masks its displacement within the broader movement of the scene. This strategy requires a continuous feedback loop between perception and action. The octopus must detect not only the static features of its surroundings, but also the dynamic changes occurring within them. Its nervous system, distributed across a central brain and multiple neural centers within its arms, processes this information in parallel, allowing for rapid, localized adjustments. Each arm can respond independently, altering its position, texture, and even color to maintain the overall illusion. The result is a form of camouflage that is not fixed, but adaptive in real time. Nearby, a predatory fish patrols the reef, its body streamlined, its movements efficient and purposeful. It scans the terrain for signs of life, its vision tuned to detect contrasts and motion that deviate from the background. As it approaches the area where the octopus rests, the tension between detection and concealment becomes immediate. The octopus does not flee. Instead, it intensifies its transformation. The papillae extend further, exaggerating the roughness of its skin. Dark patches deepen, aligning with the shadows cast by nearby coral fragments, while lighter areas adjust to match the exposed surfaces. The edges of its body soften, losing any clear boundary that might define its outline. Even the positioning of its arms changes, spreading unevenly to mimic the random distribution of debris across the reef. It becomes less like an animal and more like a continuation of the environment itself. The fish passes within a short distance, its gaze sweeping across the area. It pauses briefly, hovering as if evaluating the scene. For a moment, the success of the octopus's strategy hangs in balance. Then, the fish moves on, its attention drawn elsewhere, the illusion unbroken. The octopus remains where it is, having survived not by escaping, but by refusing to be categorized as prey. This ability to disappear in plain sight is not without its costs. Maintaining such a high level of camouflage requires constant attention and energy. The muscles controlling the chromatophores and papillae must remain active, adjusting continuously to match the environment. The nervous system must process a steady stream of sensory data, updating the camouflage as conditions change. In a sense, the octopus is always working, even when it appears still. Yet the benefits are profound. By avoiding detection altogether, the octopus reduces the need for costly escape behaviors, conserving energy and minimizing risk. It also gains the advantage of proximity. While many prey species must keep a safe distance from potential predators, the octopus can remain close, embedded within the same environment, without triggering a response. This proximity can be turned to its advantage when the roles are reversed. A small crustacean emerges from beneath a rock, its movements cautious but necessary as it searches for food. It is unaware of the octopus, which remains perfectly integrated into the surrounding texture. Slowly, almost imperceptibly, one of the octopus's arms begins to extend. The movement is subtle, synchronized with the shifting shadows, the arm's texture and coloration matching the substrate so closely that it remains indistinguishable from the background. The arm advances inch by inch until it is within reach. Then, with sudden precision, it curls around the crustacean, securing it before it can react. The rest of the body follows, enveloping the prey in a controlled, coordinated motion. The transition from stillness to action is abrupt, but by the time it occurs, the outcome is already determined. The prey had no opportunity to recognize the threat, its perception shaped by an environment that had been carefully manipulated. This dual use of camouflage, for both defense and predation, highlights the versatility of the octopus's approach. It is not simply avoiding detection. It is controlling when and how it is detected, choosing the moments to reveal itself based on opportunity. The same mechanisms that allow it to vanish can be reversed to create sudden, decisive action. Beyond immediate survival, this strategy has broader ecological implications. The octopus occupies a position within the reef that is both predator and prey, interacting with multiple levels of the food web. Its ability to avoid detection influences the behavior of predators, which must account for the possibility of unseen threats, and prey, which must navigate an environment where danger may not be visible until it is too late. In this way, the octopus contributes to the complexity of the ecosystem, adding a layer of uncertainty that shapes interactions across species. As the day progresses, the light continues to change, altering the visual landscape once more. The octopus responds accordingly, its skin shifting through a range of patterns that track the evolving conditions. In brighter light, contrasts become sharper, and the octopus increases the definition of its patterns to match. In dimmer conditions, it softens its appearance, reducing contrast to blend with the subdued environment. This continuous adjustment underscores the importance of flexibility in its strategy. There is no single correct appearance, only a constant process of matching and rematching. At times, the octopus adopts a different approach, reducing its reliance on complex patterns and instead mimicking larger, more uniform surfaces. On a sandy patch, it may flatten its body, smoothing its texture and adopting a pale, even coloration that reflects the surrounding sediment. Here, the goal is not to break up its outline, but to eliminate it entirely, becoming a featureless extension of the seafloor. The choice of strategy depends on the environment, the type of threat, and the immediate context, reflecting a level of behavioral flexibility that is rare among invertebrates. As evening approaches and the reef transitions into a different phase of activity, the octopus begins to retreat toward its shelter. The crevice it inhabits is narrow, just wide enough to accommodate its body when compressed. It flows back inside, its form adapting to the constraints of the space, its skin darkening to match the interior shadows. Even here, within the relative safety of its den, the mechanisms of camouflage remain active, ensuring that the entrance appears as unremarkable as the surrounding rock. In this final position, the octopus is both present and absent, occupying a space that is visible yet unclaimed by any recognizable form. Its existence challenges the assumptions of perception, revealing that visibility does not guarantee detection, and that identity can be as fluid as the body that carries it. In the complex, ever-changing world of the reef, where survival depends on the ability to navigate both physical and sensory challenges, the octopus has evolved a strategy that operates at the level of perception itself. It does not simply react to its environment. It becomes it, dissolving the boundary between organism and surroundings until the distinction no longer matters. Through texture matching, color blending, and the seamless integration of movement into camouflage, it achieves a form of invisibility that is not about hiding in darkness, but about existing in the open, unseen. Far from the structured complexity of coral reefs and shallow flats, the open ocean presents a different kind of challenge, one defined not by obstacles, but by absence. There are no rocks to hide behind, no crevices to retreat into, no fixed textures to mimic. Instead, there is water stretching in every direction, layered by depth and light, forming a vast three-dimensional space where exposure is constant, and concealment must be engineered in entirely different ways. Here, survival depends on managing visibility in a medium where light does not simply illuminate, but defines position, depth, and identity. In the upper layers of the open ocean, sunlight penetrates deeply, creating a gradient that shifts from bright, almost blinding illumination near the surface to dim, diffuse blue as depth increases. This gradient produces one of the most dangerous visual conditions in marine environments. For animals swimming in mid-water, their silhouettes are often visible from below, outlined against the brighter surface above. Predators positioned at greater depths scan upward, using this contrast to detect prey that would otherwise remain hidden. It is a simple but effective system. Any organism that blocks light becomes a shadow, and any shadow becomes a target. A squid moves within this layered light, its body streamlined, its fins stabilizing its position as it hovers in the water column. Unlike reef-dwelling species, it cannot rely on background matching or structural camouflage. There is nothing behind it to blend into. Instead, it must address the problem of visibility directly, altering not its shape, but the light that interacts with it. Along the underside of its body, small specialized organs begin to activate. These are photophores, biological light-producing structures that emit controlled patterns of illumination. Unlike the diffuse glow of some deep-sea organisms, the light produced here is precise, adjustable in both intensity and distribution. As the squid drifts, the photophores brighten, their output carefully calibrated to match the downwelling light from above. This process, known as counter-illumination, represents a fundamentally different approach to camouflage. Rather than hiding by reducing visibility, the squid hides by eliminating contrast. By producing light on its underside that matches the brightness and color of the surface light, it effectively erases its shadow. To an observer below, the squid no longer appears as a dark silhouette interrupting the light. Instead, it blends into the background illumination, becoming indistinguishable from the water column itself. The precision required for this strategy is remarkable. Light intensity changes continuously with depth, time of day, and water conditions. A slight mismatch between the squid's emitted light and the ambient light above could reveal its presence, creating either a darker or brighter outline that predators could detect. To maintain effective camouflage, the squid must constantly adjust its photophore output, responding to subtle changes in its environment. This adjustment is guided by highly sensitive visual systems. The squid's eyes are adapted to detect differences in light intensity and direction, allowing it to estimate the brightness of the surface above. Neural circuits process this information in real time, modulating the activity of the photophores to maintain alignment with the ambient light field. The result is a dynamic equilibrium, a continuous balancing act between emission and environment. As the squid moves vertically through the water column, this balance must be recalibrated. Descending even a short distance reduces the intensity of downwelling light, requiring a corresponding decrease in photophore output. Ascending toward the surface increases light intensity, demanding a brighter emission. These adjustments occur seamlessly, without visible delay, allowing the squid to remain concealed across a range of depths. This strategy is particularly important during diel vertical migrations, a daily movement pattern observed in many marine organisms. As daylight fades, numerous species ascend toward the surface to feed under the cover of darkness. Before dawn, they descend again, returning to deeper, darker waters to avoid predation. Squid participate in these migrations, navigating through layers of varying light conditions while maintaining their counter-illumination. The ability to adjust their bioluminescence in response to these transitions is critical for avoiding detection during both ascent and descent. Yet counter-illumination is not the only way squid use light to manipulate their visibility. In certain contexts, they employ bioluminescence more actively, using it not just to hide, but to disrupt and confuse. A predatory fish approaches from below, its eyes adapted to detect faint contrasts in the dim blue environment. It scans upward, searching for silhouettes that break the uniformity of light. The squid, aware of the approaching threat, shifts its strategy. The steady glow of its photophores begins to change, patterns emerging across its body as the light pulses and flickers. These patterns are not random. They are structured, designed to interfere with the predator's ability to track movement and determine distance. By altering the distribution and timing of its light emission, the squid creates a moving target that is difficult to interpret. The predator's visual system, tuned to detect consistent shapes and trajectories, struggles to lock onto a stable image. The squid's outline dissolves into a shifting array of light and shadow, its position uncertain. At the same time, the squid accelerates, using jet propulsion to move through the water with sudden bursts of speed. The combination of rapid movement and dynamic light patterns creates a sensory challenge for the predator, reducing the likelihood of a successful attack. In this context, bioluminescence functions as a form of visual noise, overwhelming the predator's ability to extract useful information from its surroundings. In deeper regions, where sunlight is almost entirely absent, bioluminescence takes on additional roles. Some squid species use their photophores to produce brief flashes of light when threatened, a behavior that may startle predators or attract secondary predators that could disrupt the attack. This strategy, sometimes referred to as the burglar alarm effect, introduces a layer of ecological complexity, where the presence of one predator becomes a deterrent due to the potential arrival of another. The use of light in these interactions highlights a broader principle of marine ecology. In an environment where visibility is constrained by water and depth, light becomes a primary medium of communication and deception. Organisms that can control light gain access to a set of strategies that extend beyond physical camouflage, allowing them to influence perception directly. The squid's body is uniquely suited to this task. In addition to photophores, it possesses chromatophores similar to those found in other cephalopods, enabling rapid changes in color and pattern. While these are less effective in the open water compared to structured environments, they still contribute to the overall visual display, particularly during close-range interactions. The integration of pigmentation and bioluminescence creates a multi-layered system, where different components can be combined or emphasized depending on the situation. As night falls, the ocean undergoes a transformation. The surface light fades, and the water column becomes darker, punctuated by the occasional glow of bioluminescent organisms. In this environment, the rules of visibility shift once more. Without strong downwelling light, the need for counter-illumination decreases, but the potential for active signaling increases. The squid adjusts accordingly. Its photophores, no longer required to match surface light, begin to produce more pronounced patterns. These may serve multiple functions, from communication with other squid to coordination during group movements. Some species form loose aggregations, where synchronized light displays could play a role in maintaining cohesion or signaling reproductive readiness. The exact mechanisms and meanings of these displays are still being studied, but their existence underscores the versatility of the squid's light-producing system. At the same time, the darkness introduces new risks. Predators adapted to low light conditions, including deep-sea fish and other cephalopods, rely on detecting even the faintest glimmers of light. In this context, bioluminescence can become a liability if not carefully controlled. The squid must balance the benefits of light emission with the risk of attracting unwanted attention, modulating its displays to remain effective without becoming conspicuous. As the night deepens, the squid descends slightly, entering a zone where light is scarce and the environment becomes more uniform. Here, the reliance on photophores decreases and the squid adopts a more subdued state, conserving energy while maintaining readiness for sudden movement. Its body remains streamlined, its sensory systems alert, prepared to respond to any change in its surroundings. In this vast open environment where there is nowhere to hide in the traditional sense, the squid has evolved a strategy that redefines camouflage. It does not attempt to disappear by blending into a background that does not exist. Instead, it manipulates the very medium of visibility, using light to erase its presence or to distort it beyond recognition. Through bioluminescence and counter-illumination, it transforms itself from a solid object into a controlled emission, aligning its appearance with the shifting conditions of the water column. This approach reveals a deeper understanding of survival in the open ocean. Visibility is not just about being seen or unseen, but about how light interacts with form. By controlling that interaction, the squid gains a level of influence over its own perception, shaping how it is interpreted by others in the ecosystem. In a world defined by gradients of light and the constant risk of exposure, the squid does not rely on concealment alone. It engineers invisibility through illumination, turning light itself into a tool for survival. The reef edge marks a transition zone, where structured coral formations give way to open water and scattered outcrops, creating a boundary that is neither fully sheltered nor fully exposed. It is a place of gradients, where light shifts rapidly with depth, currents accelerate along the slope, and the density of life begins to thin just enough to change the rules of interaction. In these conditions, survival depends less on outright concealment and more on perception, on how movement is interpreted, how shapes are recognized, and how risk is calculated in a constantly changing visual field. Suspended just above the reef face, a lionfish drifts forward with an almost unnatural calm. Its body is adorned with elongated fin rays that extend outward in all directions, each one tipped with venomous spines capable of delivering a painful and potentially dangerous sting. Its coloration is bold rather than subtle, marked by contrasting bands of dark and light that should, by conventional logic, make it more visible, not less. And yet, despite this apparent conspicuousness, the lionfish moves through the reef with a level of undisturbed access that many more cryptic predators never achieve. The explanation lies not in hiding, but in how the lionfish manipulates the perception of motion. Most predators in this environment rely on speed, bursts of acceleration that overwhelm prey before it can react. These movements are abrupt, easily detected, and immediately associated with danger. Prey species have evolved to recognize these cues, their nervous systems tuned to respond to sudden changes in velocity and direction. A rapid approach triggers an equally rapid escape, a reflex that has been refined over countless generations. The lionfish does the opposite. It slows everything down. As it advances, its movements are deliberate and continuous, lacking the sharp accelerations that typically signal predatory intent. Its fins undulate gently, creating a smooth flowing motion that blends with the ambient movement of the water itself. In a habitat where currents constantly shift and particles drift in slow, irregular paths, this kind of motion does not stand out. It becomes part of the background activity, something to be noted but not feared. This strategy exploits a fundamental aspect of sensory processing in many fish. Detection is not based solely on the presence of another organism, but on deviations from expected patterns of movement. Slow, consistent motion falls within the range of normal environmental variation, especially in a reef where plant life sways and invertebrates drift. By aligning its behavior with these patterns, the lionfish reduces the likelihood of triggering an escape response. At the same time, its body structure contributes to the illusion. The extended fin rays break up its outline, making it difficult for prey to identify a clear direction of movement or a defined shape. Instead of presenting as a single, coherent predator, the lionfish appears as a diffuse, expanding form, its boundaries blurred by the radial arrangement of its fins. This lack of a clear outline further complicates the prey's ability to interpret the situation, delaying the recognition of threat. A small group of juvenile fish hovers near a coral outcrop, their attention divided between feeding and maintaining awareness of their surroundings. They detect the lionfish, but their response is muted. The slow approach, combined with the absence of sudden motion, does not match the pattern of an immediate threat. Instead of fleeing, they adjust their position slightly, maintaining distance but not committing to a full escape. The lionfish continues its advance, closing the gap with steady precision. As it approaches, its fins begin to play a more active role. The pectoral fins, large and fan-like, extend outward, forming a curved barrier around the prey. This is not a random display. It is a controlled expansion that gradually reduces the available space, guiding the fish into a more confined area. This behavior creates what can be described as a false safe zone. The prey, rather than perceiving the lionfish as an immediate danger, interprets the expanding fins as a boundary that can be navigated. The space within the arc of the fins appears stable, even protected, while the open water beyond seems less predictable. In this subtle shift of perception, the lionfish redefines the spatial dynamics of the encounter. The prey begins to move inward, adjusting its position relative to the fins. Each movement brings it closer to the lionfish's mouth, though the connection is not immediately apparent. The predator does not lunge or accelerate. It simply maintains its slow advance, allowing the structure of its fins to do the work of containment. At the critical moment, the lionfish changes its behavior. The slow, deliberate motion gives way to a rapid expansion of its mouth, creating a powerful suction that draws water and the prey within it directly inward. The transition from stillness to action is sudden, but by the time it occurs, the outcome is already determined. The prey has been positioned, confined, and disoriented, its ability to escape compromised long before the final strike. This sequence reveals a key aspect of the lionfish's strategy. It does not rely on overwhelming force or speed, but on the gradual manipulation of perception and space. By reducing the cues that typically signal danger and introducing structures that alter movement patterns, it creates conditions where prey make decisions that ultimately lead them into the predator's reach. The effectiveness of this approach is amplified by the lionfish's venomous defenses. The spines that line its fins serve as a deterrent to potential predators, reducing the need for rapid escape behaviors. This allows the lionfish to maintain its slow, deliberate movements without increasing its own vulnerability. In many cases, predators that might otherwise attack a similarly sized fish will avoid the lionfish altogether, recognizing the risk associated with its spines. This combination of offensive and defensive adaptations creates a unique ecological role. The lionfish can occupy areas of the reef with relatively low competition from other predators, exploiting niches where its slow-motion strategy is particularly effective. In regions where it has been introduced outside its native range, this has led to significant impacts on local ecosystems, as native prey species, unfamiliar with its behavior, fail to recognize the threat until it is too late. The sensory basis of this interaction extends beyond vision. Many fish rely on their lateral line system, a network of sensory organs that detect water movement and pressure changes, to identify approaching predators. Rapid movements generate strong signals that can be detected even in low visibility conditions. The lionfish's slow approach minimizes these signals, reducing its detectability not only visually, but mechanically as well. By moving in a way that produces minimal disturbance, it avoids triggering multiple layers of the prey's defense system. As the lionfish continues along the reef edge, it encounters a variety of potential prey, each with its own set of sensory capabilities and behavioral patterns. Some species are more cautious, maintaining greater distance and responding more quickly to changes in the environment. Others are less vigilant, particularly juveniles or species that have not evolved alongside lionfish and lack the behavioral adaptations to recognize its unique threat profile. In each case, the lionfish adjusts its approach, modulating its speed, fin position, and trajectory to match the context. This flexibility suggests a level of behavioral control that goes beyond fixed patterns, allowing the predator to optimize its strategy based on the characteristics of its target. The environment itself plays a role in shaping these interactions. In areas with stronger currents, the background motion of the water can mask the lionfish's movement even further, enhancing the effectiveness of its slow approach. In calmer conditions, where movement is more noticeable, the lionfish may rely more heavily on its fin displays to create visual complexity and reduce the clarity of its outline. As the sun begins to lower and the angle of light changes, the reef edge becomes a different landscape. Shadows lengthen, contrasts deepen, and the visual cues that define objects shift once more. The lionfish continues its patrol, its movements unchanged, its strategy consistent. In this evolving environment, its reliance on slow, controlled motion provides a stable approach that remains effective across a range of conditions. The concept of a false safe zone, central to the lionfish's hunting strategy, reflects a broader principle in predator-prey dynamics. Survival is not determined solely by physical capabilities, but by how information is processed and interpreted. By altering the signals that prey use to assess risk, the lionfish effectively rewrites the rules of engagement, creating situations where the most adaptive response, remaining calm, maintaining position, becomes a liability. In this way, the lionfish does not just hunt within the ecosystem. It interacts with the cognitive frameworks of other organisms, exploiting the assumptions built into their behavior. Its slow-motion illusion is not about hiding or overpowering, but about guiding perception, shaping decisions in ways that favor the predator. As darkness approaches and the reef transitions into its nocturnal phase, the lionfish remains active, its strategy unchanged. In the dimmer light, its movements become even less conspicuous, its outline further softened by the reduced visibility. The false safe zones it creates become more difficult to interpret, the boundaries between predator and environment even more ambiguous. In the end, the lionfish's success lies in its ability to exist at the edge of perception. visible yet unthreatening, present yet misinterpreted. Through slow movement, controlled displays, and the manipulation of space, it transforms the act of hunting into a process of gradual influence, where the outcome is determined not by speed or ukua, but by the quiet redefinition of what is seen and what is understood. The reef shallows at low tide become a fragmented world, a mosaic of isolated pools, exposed rock, and shallow channels that pulse with residual currents. Water lingers in depressions carved by time and erosion, forming still basins where life is compressed into tight, unavoidable proximity. The surface above is calm, almost glass-like, but beneath it, tension builds quietly. Every organism here is visible, every movement amplified by the lack of depth, and every mistake immediately punished. In such an exposed environment, survival depends not on escape routes or speed, but on the ability to disappear so completely that even direct contact fails to reveal the truth. Resting among a cluster of irregular rocks, one form appears indistinguishable from the rest. Its outline is uneven, its surface mottled with browns, greys, and muted greens that blend seamlessly with the surrounding substrate. Patches of filamentous algae cling to its body, softening edges, breaking continuity, and adding a layer of biological noise that reinforces the illusion. Small encrusting organisms, including bits of sponge and microbial films, contribute further to the disguise, embedding the animal into the ecological fabric of the reef. It does not simply resemble a rock. It has become one, both visually and functionally. This is the stonefish, an organism that has taken camouflage to its most extreme conclusion. Where other animals rely on dynamic adjustments, shifting colors and textures in response to changing conditions, the stonefish commits to permanence. Its body is structured for stillness, its camouflage so precise that movement becomes unnecessary, even undesirable. In this strategy, the absence of action is not a limitation, but a deliberate and highly refined choice. The skin of the stonefish is not smooth or uniform. It is a complex surface, layered with folds, ridges, and protrusions that mirror the irregular geometry of the reef floor. These structures are not randomly arranged. They follow patterns that align with the types of rocks and coral fragments found in its environment, creating a three-dimensional match that extends beyond color into form. The coloration itself is equally nuanced, a mixture of pigments that produce subtle variations across the body, mimicking the way light interacts with natural surfaces over time. Unlike many camouflaged animals, the stonefish does not rely on rapid changes to maintain its disguise. Its appearance is relatively fixed, optimized for the specific habitat it occupies. This specialization reflects a different evolutionary pathway, one that favors precision over flexibility. By committing to a particular environment, the stonefish achieves a level of mimicry that is difficult to surpass, but at the cost of reduced adaptability to changing conditions. Positioned within a shallow pool, the stonefish remains motionless. Water flows gently around it, carrying fine particles that settle across its surface, further integrating it into the surroundings. Small fish move through the pool, navigating between rocks and patches of algae, their attention focused on feeding and avoiding more obvious threats. To them, the stonefish is not an object of interest. It is part of the landscape, a stable element that requires no consideration. This zero-movement strategy is central to the stonefish's success. Movement, even slight, introduces discrepancies between an organism and its environment, creating cues that can be detected by visual or mechanical sensory systems. By eliminating movement entirely, the stonefish removes one of the primary signals that predators and prey use to identify living organisms. It becomes a static feature, indistinguishable from the inert objects around it. Yet beneath this still exterior lies a highly specialized predatory system, one that is designed to operate with sudden, explosive efficiency when the moment arrives. The stonefish's mouth is positioned upward, its jaws capable of opening with remarkable speed. When prey comes within range, the fish can generate a powerful suction force, drawing water and the unsuspecting organism into its mouth in a fraction of a second. The transition from absolute stillness to rapid action is abrupt, but by the time it occurs, the prey is already within reach. a small fish approaches, its movements cautious but routine. It navigates the pool, weaving between rocks, occasionally pausing to inspect the substrate for food. As it nears the stonefish, there is no change in its behavior. The predator presents no recognizable cues, no outline that suggests danger, no motion that triggers an alarm. The fish continues forward, closing the distance until it is directly above the stonefish's head. In this moment, the effectiveness of the stonefish's strategy becomes evident. The prey does not avoid the predator. It interacts with it, swimming over and around it as if it were a harmless object. This is not merely a failure of detection. It is a consequence of a system where the cues used to identify threats have been completely neutralized. The strike, when it comes, is instantaneous. The stonefish's jaws open, creating a sudden vacuum that pulls the fish downward. Water rushes inward, carrying the prey with it, and the jaws close just as quickly, sealing the outcome. The entire event occurs so rapidly that it leaves little trace, the surrounding water settling back into stillness as if nothing had happened. This method of predation relies on proximity rather than pursuit. The stonefish does not chase its prey. It allows the prey to come to it, exploiting the normal behaviors of organisms that must constantly forage and move within their environment. By positioning itself in areas where prey are likely to pass, it increases the probability of encounters without expending energy on active hunting. The ecological implications of this strategy are significant. In a system where many predators rely on active pursuit, the stonefish represents a different kind of threat, one that operates through ambush and deception at the highest level. Its presence influences the behavior of prey species, which must navigate environments where danger is not always visible or predictable. Over time, this can lead to changes in movement patterns, habitat use, and even sensory adaptations, as species evolve to better detect or avoid such hidden predators. Beyond its role as a predator, the stonefish is also equipped with one of the most potent venom systems among fishes. Along its dorsal surface, a series of spines are connected to venom glands that can deliver a powerful toxin when pressure is applied. This defense is not used actively, but serves as a deterrent to potential predators and an additional layer of protection in its exposed habitat. The venom can cause severe pain and physiological effects in larger animals, including humans, making the stonefish a creature that commands caution even among species that might otherwise prey on it. This dual strategy, extreme camouflage combined with potent defense, allows the stonefish to maintain its position in a highly competitive and exposed environment. It does not need to flee from threats, nor does it need to reveal itself to hunt. Instead, it occupies a narrow but highly effective niche, one that minimizes energy expenditure while maximizing success. The sensory world of the stonefish is adapted to support this lifestyle. While it remains motionless, it must still detect changes in its environment, identifying the approach of prey or potential threats. Its lateral line system is sensitive to vibrations and pressure changes in the water, allowing it to perceive movement without relying on vision alone. This is particularly important in the shallow pools, where visibility can be affected by sediment and fluctuating light conditions. As the tide begins to rise, the isolated pools reconnect with the larger body of the reef. Water flows in, bringing new organisms and altering the dynamics of the environment. The stonefish remains in place, its strategy unchanged. The increased movement of water and life around it does not disrupt its camouflage. Instead, it enhances it, adding layers of motion and complexity that further obscure its presence. In these changing conditions, the stonefish continues to function as both predator and hidden hazard, an organism that challenges the very concept of visibility. It demonstrates that in certain environments, the most effective way to survive is not to adapt continuously, but to become so perfectly aligned with a specific context that adaptation becomes unnecessary. As the water deepens and the reef returns to its submerged state, the stonefish remains where it has always been, a silent participant in the ecosystem, influencing interactions without revealing itself. Its existence is a reminder that in the natural world, danger is not always marked by movement or obvious signals. Sometimes it lies in stillness, in forms that blend so completely with their surroundings that they cease to be recognized as living at all. In the end, the stonefish's invisibility is not an absence of presence, but a transformation of it. It occupies space, interacts with its environment, and shapes the behavior of other organisms, all while remaining unseen. Through perfect rock mimicry, algae-covered skin, and an unwavering commitment to stillness, it achieves a level of concealment that turns the act of perception itself into a challenge, redefining what it means to be visible in the underwater world. Along the temperate coasts where cold currents sweep nutrients across submerged forests, the seafloor gives way to a different kind of architecture. Here, towering kelp rises from rocky anchors, stretching upward in long, flexible columns that sway with the rhythm of the ocean. The water is often dimmer than tropical reefs, tinted green by dense plant growth and suspended particles. Visibility shifts constantly as fronds overlap, fold and drift, creating a layered environment where movement is slow, fluid, and rarely linear. In this underwater forest, survival is not about speed or aggression. It is about fitting into a system defined by perpetual motion without ever appearing separate from it. Drifting among these columns of kelp, something moves with such precision that it is nearly impossible to isolate from the background. Its body is elongated and slender, but its outline is obscured by a series of leaf-like appendages that extend outward in irregular patterns. These structures do not propel the animal. They do not assist in swimming or feeding. Instead, they exist purely for appearance, breaking up the body's form and replicating the fragmented silhouette of drifting seaweed. This is the leafy sea dragon, an organism that has taken mimicry beyond resemblance and into near-perfect imitation. At first glance, there is no distinction between the animal and the surrounding vegetation. The appendages match the color, shape, and even the translucency of kelp fronds, catching light in the same uneven way, creating highlights and shadows that shift as the water moves. The body itself is narrow and rigid compared to the flowing appendages, but this structure is concealed by the density of the projections, which extend far enough to disrupt any clear sense of where the organism begins or ends. Unlike many marine animals that rely on active camouflage, the leafy sea dragon does not change its appearance in real time. Its strategy is fixed, embedded in its anatomy. This reflects a different evolutionary path, one that prioritizes precision over adaptability. The environment it inhabits is relatively stable in its visual characteristics. Kelp forests, while dynamic in motion, maintain a consistent palette of colors and textures. By evolving to match this environment so closely, the sea dragon achieves a level of camouflage that requires no adjustment. Movement, however, presents a challenge. Even the most accurate visual mimicry can be undermined by motion that does not align with the surrounding environment. In a forest of kelp, where every frond sways in response to currents, any deviation from this pattern can reveal an organism's presence. The leafy sea dragon addresses this by limiting its own movement to match the flow of the water itself. Its propulsion comes from small, nearly transparent fins that beat rapidly but subtly, producing just enough force to maintain position or adjust orientation. These movements are so fine and controlled that they do not disrupt the overall impression of drifting vegetation. Instead of swimming in a directed, purposeful manner, the sea dragon allows itself to be carried by the current, its body and appendages moving in synchrony with the surrounding kelp. It does not resist the flow. It becomes part of it. This approach transforms motion from a liability into an asset. By aligning its movement with that of the environment, the sea dragon ensures that its presence does not introduce new patterns that might attract attention. To an observer, it is simply another piece of seaweed, subject to the same forces, following the same trajectories. A small predatory fish moves through the kelp forest, navigating between fronds with practiced ease. Its eyes scan for prey, detecting subtle differences in shape, color, and movement. In this environment, recognition is not straightforward. The constant motion of the kelp creates a visual field where objects overlap and shift, making it difficult to isolate individual forms. The fish relies on experience, on patterns learned over time, to distinguish between edible organisms and inanimate structures. As it passes near the sea dragon, there is no change in its behavior. The predator does not slow, does not alter its path, does not investigate. The sea dragon has not triggered any of the cues that would mark it as prey. It has not hidden. It has not fled. It has simply remained unrecognized. This lack of recognition is the core of its survival strategy. In many predator-prey interactions, detection is followed by identification, and identification leads to action. By preventing the first step, detection, the sea dragon removes itself from the sequence entirely. It exists within the predator's field of view, but outside its awareness. The effectiveness of this strategy depends on the sensory limitations of other organisms. Visual systems are not designed to process every detail of the environment with equal attention. Instead, they prioritize features that stand out, that deviate from the background. The leafy sea dragon exploits this by ensuring that it does not present any such deviations. Its color matches, its shape aligns, and its movement integrates seamlessly with the surrounding vegetation. This approach is particularly effective in environments where structural complexity is high. In the kelp forest, where overlapping fronds create a dense visual field, the ability to blend into the background is enhanced by the sheer volume of similar shapes and movements. The sea dragon does not need to be perfect in isolation. It only needs to be indistinguishable within the context of its environment. Feeding within this system requires a different kind of interaction. The sea dragon is not an active hunter in the traditional sense. It does not pursue prey or engage in rapid strikes. Instead, it feeds on small crustaceans, drawing them into its elongated snout through suction. This feeding mechanism is subtle, requiring close proximity and precise timing. As the sea dragon drifts, it encounters small planktonic organisms and juvenile crustaceans carried by the current. These prey items are not actively avoiding the sea dragon, as they do not recognize it as a threat. The sea dragon positions itself within the flow, aligning its body with the direction of movement, allowing prey to come within range. When an organism approaches closely enough, the sea dragon makes a slight adjustment, a minimal movement that brings its snout into position. The suction is quick and controlled, drawing the prey inward without creating a disturbance that might reveal its presence. This method of feeding is consistent with its overall strategy. It does not seek to dominate its environment through force or speed. Instead, it operates within the existing dynamics, using the movement of water and the behavior of prey to its advantage. By remaining unrecognized, it gains access to resources without triggering defensive responses. The reproductive behavior of the leafy sea dragon introduces another layer of complexity. Unlike many fish species, where eggs are released into the water or attached to substrates, the male sea dragon carries the fertilized eggs on the underside of its tail. These eggs are attached to a specialized brood patch, where they remain exposed but protected by the male's presence. This arrangement requires the male to maintain its camouflage while carrying a cluster of developing offspring, each one potentially altering the outline and texture of its body. The eggs themselves are often colored in ways that blend with the surrounding appendages, integrating into the overall illusion. The male continues to drift within the kelp forest, its movements unchanged, ensuring that both it and its developing young remain unrecognized. This form of parental care highlights the importance of camouflage not just for individual survival, but for reproductive success. The ability to remain undetected extends to the next generation, providing a level of protection during a vulnerable stage of development. As conditions in the kelp forest change with tides and weather, the sea dragon's reliance on its environment becomes more apparent. Strong currents can alter the distribution of kelp, changing the density and arrangement of the vegetation. Storms can damage or remove sections of the forest, reducing the available cover. In such situations, the sea dragon's specialized camouflage may become less effective, exposing it to increased risk. This dependency underscores a trade-off inherent in its strategy. By evolving such a precise match to a specific environment, the sea dragon achieves exceptional camouflage under normal conditions, but becomes more vulnerable when those conditions are disrupted. Its survival is closely tied to the health and stability of the kelp ecosystem, making it an indicator of environmental change. As the day progresses and light filters through the water at different angles, the appearance of the kelp forest shifts. Shadows deepen, highlights move, and the overall color palette changes subtly. The sea dragon remains within this shifting environment, its fixed appearance continuing to align with the general characteristics of the vegetation. The lack of rapid change in its coloration is offset by the consistency of the kelp's visual properties, allowing the illusion to persist across varying conditions. In the quiet, swaying world of the kelp forest, the leafy sea dragon embodies a different kind of survival. It does not compete through speed or aggression. It does not adapt moment by moment. Instead, it exists as a perfect echo of its environment, a living extension of the plants that surround it. Through plant illusion, it achieves a state where recognition is bypassed entirely. Predators do not ignore it because they choose to. They ignore it because they never identify it as something worth noticing. In this subtle but profound way, the sea dragon reveals that survival in complex ecosystems is not always about being the fastest or the strongest. Sometimes, it is about becoming so deeply integrated into the environment that the distinction between organism and surroundings dissolves, leaving behind only the movement of water and the quiet persistence of life hidden within it. The tide has just begun to fall along a shallow tropical reef flat, revealing a shifting mosaic of sand ripples, broken coral, and scattered debris that seems, at first glance, lifeless. The water here is warm and thin, barely deep enough to cover the backs of grazing fish, and exposed enough that every movement risks detection. It is a place where visibility works against survival, where predators patrol from above and below, and where concealment is not a luxury, but a requirement written into the biology of everything that lives here. Yet in this open, exposed landscape, something moves with a confidence that appears almost reckless. A small, soft-bodied creature crosses the sand in broad daylight, leaving behind delicate trails as its arms extend and retract in smooth, deliberate motion. It is not hiding. It is not blending in. It is, in a sense, performing. This is the mimic octopus, a species that has taken one of evolution's most common tools, camouflage, and turned it into something far more dynamic and unsettling. Most animals disappear by becoming less noticeable, by dissolving into their surroundings until the eye passes over them without recognition. But this animal does the opposite. It becomes something else entirely, not just in color or texture, but in form, posture, and behavior. It does not merely hide, it lies. The body of the mimic octopus is built on a foundation of extreme flexibility, but that alone does not explain what is happening here. Like other octopuses, it possesses specialized skin cells called chromatophores that expand and contract to change color in fractions of a second. Beneath these lie layers of reflective cells that can alter brightness and iridescence, and deeper still, muscular hydrostats that allow the animal to reshape its entire body without bones or rigid structures. This combination creates a system capable of near infinite variation. Yet what separates this species from others is not the hardware, but the decision-making layered on top of it. The mimic octopus does not simply react to its environment, it interprets it. As it moves across the sand, a shadow passes overhead. The change is subtle, a slight dimming of light as something larger crosses between the sun and the sea floor. For many animals, this would trigger an immediate freeze response or a rapid retreat into shelter. But the mimic octopus responds differently. Its arms begin to draw inward, then extend in a precise, controlled arrangement. The body flattens, elongates, and spreads across the substrate. Within seconds, the animal no longer resembles an octopus at all. Instead, it takes on the shape and movement of a flatfish, gliding low against the sand with undulating motions that mimic the swimming pattern of a completely different species. This is not random. The choice of disguise is tied directly to the type of threat detected. Flatfish are generally ignored by many predators that would otherwise prey on a soft-bodied cephalopod. By adopting this form, the octopus does not become invisible. It becomes uninteresting. And in an ecosystem where attention often determines survival, that distinction is everything. The transformation goes beyond simple shape. The octopus adjusts its coloration to match the mottled patterns typical of benthic fish, aligning not just its appearance but its behavior with the identity it is assuming. Its movement slows, becoming rhythmic and predictable, matching the ecological role of the organism it is imitating. This alignment of form and function is critical. A disguise that looks correct but behaves incorrectly would fail under scrutiny. Predators are not passive observers. They are experienced evaluators of movement, timing, and context. The mimic octopus succeeds because it understands, in a biological sense, the rules of the system it is manipulating. Moments later, the shadow disappears, and with it, the immediate threat. The octopus relaxes its body, the flat shape dissolving back into a more familiar form as its arms regain independence. It resumes its forward movement, exploring the sand with sensory suckers that taste and feel simultaneously. Each contact provides chemical and tactile information, allowing the animal to map its environment in a way that vision alone cannot achieve. This constant stream of data feeds into its decision-making process, informing not just where it moves, but how it presents itself to the world. Further along the reef flat, the terrain changes. Patches of seagrass begin to appear, their thin blades swaying gently with the current. This area introduces a different set of risks and opportunities. The vertical structure provides cover, but also limits visibility, creating zones where ambush predators can remain hidden until the last possible moment. It is here that the mimic octopus demonstrates another layer of its adaptive strategy. As it approaches the grass, its posture shifts again. Two of its arms extend outward and backward, held rigid and slightly raised, while the remaining arms tuck closer to the body. The coloration changes dramatically, alternating bands of dark and light running along the length of its extended limbs. The transformation is striking. The animal now resembles a venomous sea snake, a predator in its own right, known for its potent neurotoxic venom and aggressive defense when threatened. This particular disguise targets a different audience. While some predators might ignore a flat fish, they would actively avoid a sea snake. The cost of misidentifying such a creature is too high. Even a brief encounter could result in envenomation, leading to paralysis or death. By presenting itself as a dangerous organism, the octopus shifts the risk calculation of any potential predator. It is no longer a meal. It is a potential threat. What makes this behavior remarkable is not just the physical transformation, but the apparent context in which it is deployed. The mimic octopus does not use all of its disguises indiscriminately. Instead, it appears to select specific identities based on the type of predator it perceives. Observations in the wild have shown that when confronted with certain fish species, it is more likely to adopt the sea snake form, while in other situations, it may choose a different mimic altogether. This suggests a level of environmental assessment and response that goes beyond simple stimulus-response patterns. It implies a flexible strategy, one that can be adjusted in real time based on changing conditions. The ability to mimic a lionfish adds yet another dimension to this system. Lionfish are equipped with venomous spines and a distinctive flared appearance that signals danger to other animals. When the mimic octopus adopts this form, it spreads its arms outward, creating a radial silhouette that echoes the spines of the fish. Its coloration shifts to match the contrasting patterns, and its movement becomes slow and deliberate, mirroring the hovering behavior of the original species. Again, the goal is not invisibility, but deterrence through misidentification. Underlying all of these transformations is a complex interplay between physiology, perception, and ecological context. The octopus must first detect a potential threat, then categorize it in a way that informs its choice of disguise. It must then execute a precise series of muscular and chromatophoric changes to achieve the desired appearance, all while maintaining behavior that reinforces the illusion. Each step requires coordination across multiple systems, from sensory input to motor output, operating on timescales that leave little room for error. This level of integration highlights a broader principle in evolutionary biology. Adaptations are rarely isolated traits. They are networks of interacting features that together create a functional outcome. In the case of the mimic octopus, its shape-shifting ability is not just about flexible skin or complex muscles. It is about the coupling of those physical traits with a behavioral repertoire that gives them meaning. Without the correct behavior, the physical transformation would be incomplete. Without the physical capacity, the behavior would be impossible. As the tide continues to recede, the environment becomes even more exposed. Pools of water are left behind, isolated from the main body of the ocean. In these confined spaces, the dynamics of predation intensify. There is less room to escape, fewer places to hide, and a higher concentration of both predators and prey. It is in these conditions that the mimic octopus's strategy reaches its most extreme expression. Trapped in a shallow pool with a predatory fish, the octopus cannot rely on distance or concealment. Instead, it escalates its deception. Its body elongates dramatically, arms trailing behind in a configuration that exaggerates the appearance of a sea snake. The movement becomes more pronounced, the undulations sharper, creating a visual signal that is difficult to ignore. The predator hesitates. In that hesitation lies the octopus's survival. This interaction illustrates a critical aspect of mimicry. It does not need to be perfect. It only needs to be convincing enough to trigger the appropriate response in the observer. The predator does not conduct a detailed analysis. It operates on heuristics, quick assessments based on shape, movement, and pattern. If enough of those cues align with a known dangerous species, the safest choice is avoidance. The mimic octopus exploits this cognitive shortcut, inserting itself into the decision-making process of another animal. At the same time, this strategy carries its own risks. Mimicry is effective only within a specific ecological context. If the predator has prior experience that contradicts the illusion, or if the environmental conditions make the disguise less convincing, the octopus could be exposed. Additionally, the act of transforming and maintaining a disguise requires energy and attention, resources that could otherwise be used for foraging or reproduction. The balance between these costs and benefits shapes how and when the octopus deploys its various identities. Beyond predator avoidance, there is evidence that this form of mimicry may also play a role in hunting. By adopting the appearance of a harmless or even predatory species, the octopus can approach potential prey without triggering an escape response. Small fish or crustaceans that would flee from an octopus might ignore a flatfish or misinterpret the signals of a different organism, allowing the octopus to close the distance before striking. In this way, identity theft becomes a dual-purpose tool, serving both defense and offense. The existence of such a system challenges simple categorizations of animal behavior. It blurs the line between camouflage and communication, between instinct and decision. The mimic octopus does not just blend into its environment. It manipulates the perceptions of other organisms, inserting false information into the ecological network. It becomes a moving piece of misinformation, reshaping interactions in real time. As the sun lowers and the tide begins to return, the reef flat is gradually submerged once more. The mimic octopus retreats toward deeper water, its movements becoming less exposed, its need for dramatic transformation reduced. In the shifting light and rising water, it becomes just another shadow among many, its extraordinary abilities hidden beneath the surface. Yet the impact of its strategy remains. In a world where survival often depends on being seen or not seen, the mimic octopus occupies a third category. It is seen, but not as itself. It survives not by disappearing, but by rewriting the identity that others perceive. In doing so, it reveals a deeper truth about life in complex ecosystems. Sometimes, the most effective way to avoid danger is not to hide from it, but to become something it fears. In the quieter margins of coastal ecosystems, where currents slow and sediments settle, vast meadows of seagrass stretch across the seafloor like submerged fields. The water here carries a different texture than the open reef, softer, denser with suspended particles that scatter light into a muted green haze. Visibility is reduced not by darkness, but by diffusion. Shapes blur at their edges, and movement is absorbed into the gentle sway of vegetation that bends in slow, synchronized arcs under the influence of tidal flow. It is a landscape defined by vertical lines, slender blades rising from the sediment and moving together in a rhythm that is both constant and deceptively uniform. Within this vertical world, orientation becomes a critical factor in perception. Most fish move horizontally, their bodies aligned with the direction of travel, their silhouettes cutting across the vertical structure of the grass. This contrast makes them easier to detect, their movement breaking the pattern of the environment. But not all organisms follow this rule. Some have evolved to align themselves with the structure of the habitat itself, transforming their orientation into a form of camouflage. A seahorse drifts among the blades, its body held upright, its head angled slightly downward as if observing the ground below. Its shape is unlike that of most fish. Its body elongated and curved, its tail coiled and capable of gripping onto stems. The bony plates that form its external structure give it a rigid, almost armored appearance. Yet its movement is subtle, controlled by a small dorsal fin that beats rapidly, producing just enough force to maintain position without generating noticeable disturbance. At first glance, the seahorse appears stationary, its vertical posture blending seamlessly with the surrounding vegetation. Its coloration matches the tones of the seagrass, shifting subtly between greens, browns, and muted yellows, depending on the local conditions. Small filamentous extensions along its body mimic the irregularities of plant surfaces, further breaking up its outline. It does not attempt to hide behind the grass. It becomes another blade within it. The effectiveness of this strategy lies in how visual systems interpret orientation and movement. Predators and prey alike are attuned to deviations from expected patterns. In a seagrass meadow, vertical elements that sway with the current are the norm. Horizontal movement, especially rapid or erratic, stands out as a potential signal of life. By aligning its body vertically and limiting its movement to the same slow oscillations as the grass, the seahorse avoids triggering these detection mechanisms. This alignment is not passive. The seahorse actively adjusts its position in response to the current, using its tail to anchor itself to a blade of grass when necessary, stabilizing its body against stronger flows. When it releases its grip, it does not swim away in a straight line. Instead, it allows itself to drift, its movement guided by the same forces that move the surrounding vegetation. The transition between anchored and free-floating states is smooth, maintaining the continuity of the illusion. Its eyes, capable of moving independently, scan the environment with a level of precision that contrasts with the apparent stillness of its body. One eye tracks the movement of small crustaceans drifting through the water, while the other monitors the broader surroundings for potential threats. This dual focus allows the seahorse to maintain awareness without altering its posture, a critical feature in an environment where even slight changes in orientation could reveal its presence. Feeding within this system is an exercise in timing and precision rather than pursuit. The seahorse does not chase its prey. Instead, it waits, positioning itself within the flow of water where small organisms are likely to pass. Its elongated snout functions as a narrow tube, capable of generating a rapid suction force that draws in prey at close range. This feeding mechanism is highly specialized, requiring the prey to be within a very short distance for successful capture. As a small crustacean drifts past, carried by the gentle current, the seahorse remains motionless. Its body sways in unison with the grass, its presence indistinguishable from the surrounding vegetation. The prey does not react, its sensory systems tuned to detect movement and contrast, neither of which the seahorse presents. Only when the crustacean is within reach does the seahorse act. The movement is minimal, a slight adjustment of the head, followed by a rapid expansion of the buccal cavity that creates a localized vacuum. Water and prey are drawn into the snout in an instant, the entire action occurring without a noticeable displacement of the seahorse's body. The surrounding water settles quickly, and the seahorse resumes its previous posture, the event leaving little trace in the environment. This ambush feeding strategy is closely tied to the seahorse's overall approach to survival. By minimizing movement and aligning with the structure of the habitat, it reduces the likelihood of detection while maintaining access to a steady flow of prey. The energy cost of this method is relatively low compared to active hunting, allowing the seahorse to sustain itself in environments where food resources may be dispersed and unpredictable. The ecological context of the seagrass meadow further enhances the effectiveness of this strategy. These habitats are nurseries for many marine species, providing shelter and feeding grounds for juvenile fish and invertebrates. The density of life creates a constant flow of potential prey, but also increases the complexity of the visual environment. In such conditions, the ability to remain unrecognized becomes a significant advantage. Predators moving through the meadow face similar challenges. Their vision must filter through layers of moving vegetation, distinguishing between living organisms and the background. The seahorse's vertical posture and synchronized movement exploit these limitations, allowing it to remain within the predator's field of view without being identified as prey. At the same time, the seahorse's own vulnerability is mitigated by this same strategy. Its rigid body and limited swimming speed would make it an easy target in open water, but within the seagrass, these traits are less of a disadvantage. By avoiding detection altogether, it reduces the need for rapid escape responses, relying instead on its integration into the environment for protection. Reproduction in seahorses introduces an additional layer of biological complexity that intersects with their camouflage. Males carry fertilized eggs within a specialized brood pouch, where the developing embryos are protected and supplied with oxygen and nutrients. This arrangement requires the male to maintain its stealth posture while carrying a load that alters its body shape and potentially its buoyancy. The brood pouch expands as the embryos develop, changing the profile of the seahorse. Yet even with this alteration, the animal continues to align itself with the vertical structure of the grass, its coloration and posture compensating for the increased volume. The ability to maintain camouflage during this period is critical, as the energetic demands of reproduction limit the seahorse's capacity for movement and escape. The physiology of the seahorse reflects its specialized lifestyle. Its swim bladder, responsible for buoyancy control, must be finely tuned to maintain its vertical position without constant fin movement. Small adjustments in gas volume allow the seahorse to remain suspended at a specific depth, reducing the need for active swimming. This control is essential in an environment where vertical alignment is key to camouflage. However, this system also introduces vulnerabilities. Changes in pressure, temperature, or water quality can affect buoyancy, making it more difficult for the seahorse to maintain its position. In such cases, the animal must expend additional energy to compensate, potentially increasing its visibility and risk of detection. As the day progresses, light filtering through the water shifts in intensity and direction, altering the appearance of the seagrass meadow. Shadows move across the blades, highlights flicker, and the overall color palette changes subtly. The seahorse remains within this dynamic environment, its camouflage adapting not through rapid change, but through its consistent alignment with the dominant structures and movements. In stronger currents, the sway of the grass becomes more pronounced, and the seahorse adjusts its grip and posture to maintain synchronization. In calmer conditions, it may release its hold more frequently, drifting between blades in a controlled manner that preserves the illusion of being part of the vegetation. This constant interplay between organism and environment highlights a fundamental aspect of the seahorse's strategy. It does not impose itself on the habitat. It conforms to it, using the existing patterns of movement and structure to define its own behavior. In doing so, it achieves a form of stealth that is not based on hiding or deception in the traditional sense, but on alignment and integration. As evening approaches and the light begins to fade, the seagrass meadow takes on a different character. The reduced visibility softens contrasts, making it even more difficult to distinguish individual forms. The seahorse continues its quiet existence within this environment, its presence neither announced nor concealed, simply unrecognized. In this world of vertical lines and gentle motion, survival is not about outpacing threats or overpowering prey. It is about existing within a narrow band of perception, where movement is minimal, orientation is precise, and identity is obscured by similarity. Through its stealth posture, vertical alignment, and near-invisible movement, the seahorse demonstrates that in certain ecosystems, the most effective strategy is not to stand out, but to disappear into the pattern so completely that recognition never occurs. In the quieter corners of the reef, where coral structures collapse into rubble fields and growth becomes irregular and layered, the environment takes on a different kind of complexity. Here, nothing is clean or symmetrical. Surfaces are broken, overgrown, and partially buried beneath sediment. Sponges expand into amorphous masses, algae coat every available surface, and fragments of once living coral stack into uneven formations that create a landscape without clear boundaries. It is a place where shapes dissolve into one another, where identity is obscured not by darkness, but by excess detail. In this cluttered world, recognition becomes difficult, and organisms that can exploit that difficulty gain an advantage that is not immediately obvious. Resting on a piece of encrusted rubble, something appears to be part of this disordered environment. Its body is irregular, lacking the streamlined form typically associated with fish. Instead, it is compact and uneven, covered in a textured skin that resembles sponge tissue more than scales. Small projections extend from its surface, mimicking the growth patterns of surrounding organisms. Its coloration is highly variable, ranging from muted yellows and greens to darker browns and reds, often matching the dominant tones of the immediate environment. At a glance, there is no clear indication that this is an animal at all. This is the frogfish, an ambush predator that has taken camouflage beyond resemblance into a deeper level of perceptual manipulation. It does not merely blend into its surroundings, it removes itself from the category of fish entirely, presenting a form that does not trigger the recognition systems of other organisms. In doing so, it achieves a kind of invisibility that operates not through concealment, but through misclassification. The body of the frogfish is built for this purpose. Its skin is thick and often covered in dermal appendages that vary in size and shape, creating a surface that mimics the irregularities of sponges, algae, or encrusted rock. These structures are not decorative. They disrupt the outline of the animal, breaking it into fragments that align with the chaotic patterns of the reef. The eyes, though capable of independent movement, are small and often partially obscured by surrounding textures, reducing the likelihood that they will be recognized as sensory organs. Unlike many fish, the frogfish does not rely on continuous swimming to maintain its position. Its pectoral fins have evolved into limb-like structures that allow it to move across the substrate in a manner that resembles walking more than swimming. This mode of locomotion is slow and deliberate, involving a sequence of small steps that shift the body forward without creating the fluid, streamlined motion typical of other fish. In an environment where most movement is either drifting with currents or rapid and directional, this stepping behavior introduces a different pattern, one that aligns more closely with the slow expansion of sponges or the gradual shifting of debris. The absence of typical swimming behavior is critical to the frogfish's illusion. Predators and prey alike are attuned to the characteristic movements of fish, their sensory systems tuned to detect the oscillations of fins and the propulsion patterns that define aquatic locomotion. By moving in a way that does not match these patterns, the frogfish avoids triggering recognition. It is not seen as a fish because it does not behave like one. Positioned among the rubble, the frogfish remains still, its body blending seamlessly with the surrounding structures. The water around it carries small particles and drifting organisms, creating a constant flow of potential prey. Unlike active hunters that pursue their targets, the frogfish relies on a different strategy, one that combines its camouflage with a specialized feeding mechanism. Extending from its head is a modified dorsal spine, known as an ilichium, which functions as a fishing rod of sorts. At its tip is a fleshy appendage called the esker, often shaped and colored to resemble small prey items, such as worms or crustaceans. This lure is not static. It moves in subtle, controlled motions, mimicking the behavior of living organisms and attracting the attention of nearby fish. A small fish approaches, drawn by the movement of the lure. Its sensory systems detect the oscillations, interpreting them as a potential food source. The surrounding environment offers no indication of danger. The frogfish's body remains indistinguishable from the substrate, its presence masked by its resemblance to inanimate structures. The prey focuses on the lure, closing the distance with cautious but steady movements. As the fish nears, the frogfish maintains its stillness, allowing the lure to do the work of attraction. The positioning is precise, the lure held just far enough from the mouth to guide the prey into an optimal location for capture. The fish, unaware of the predator's true nature, continues its approach, its attention fixed on the apparent opportunity. The strike, when it occurs, is among the fastest in the animal kingdom. The frogfish's mouth expands rapidly, creating a powerful suction that draws water and prey inward with extraordinary speed. The entire event unfolds in a fraction of a second, too fast for the prey to react. The transition from complete stillness to explosive action is abrupt, but by the time it happens, the outcome is already determined. This feeding mechanism is supported by a highly specialized jaw structure, capable of expanding to a size that far exceeds the apparent dimensions of the head. The rapid intake of water generates a force that pulls prey directly into the mouth, bypassing the need for pursuit or struggle. Once captured, the prey is swallowed whole, the frogfish returning almost immediately to its previous state of stillness. The combination of lure-based attraction and rapid suction feeding creates a system where the frogfish controls both the initiation and the outcome of the interaction. It does not need to chase or corner its prey. Instead, it creates a scenario where the prey willingly enters the zone of capture, guided by signals that exploit its natural feeding behavior. The ecological implications of this strategy are significant. In a reef environment where many predators rely on speed and visibility, the frogfish introduces a different dynamic, one that operates through deception at multiple levels. Its presence affects the behavior of prey species, which must navigate a landscape where not all threats are identifiable through conventional cues. At the same time, the frogfish's own vulnerability is mitigated by its camouflage. Larger predators that might otherwise target it are less likely to recognize it as prey, its irregular shape and lack of movement reducing the likelihood of detection. The thick skin and, in some species, the presence of toxic compounds provide additional layers of defense, making it an unappealing target even if it is discovered. The sensory world of the frogfish is adapted to support its ambush lifestyle. Its eyes, though not as prominent as those of more active hunters, are capable of detecting movement within a limited range, allowing it to monitor the area around its lure. Its lateral line system senses vibrations and pressure changes, providing information about the approach of both prey and potential threats. These inputs are integrated to determine the optimal moment for striking, ensuring that energy is not wasted on unsuccessful attempts. As the reef environment changes with the movement of water and light, the frogfish remains largely unaffected. Its camouflage is not dependent on precise alignment with a single background, but on its integration into a range of textures and colors. This flexibility allows it to maintain its illusion across different conditions, whether in brighter, clearer water or in more turbid, low-visibility environments. The concept of "I am not a fish" is central to understanding the frogfish's strategy. It does not attempt to hide within the category of fish. It removes itself from that category entirely, presenting a form that is interpreted as something else. This misclassification is more effective than simple camouflage because it bypasses the recognition process at a fundamental level. The observer does not just fail to see the frogfish. It fails to consider it as a potential organism at all. As the day progresses and the light shifts across the reef, the frogfish remains in its chosen position, its body unchanged, its presence undetected. The surrounding environment continues its activity, fish moving in and out of view, currents carrying particles and organisms through the water. Within this dynamic system, the frogfish operates as a fixed point, a hidden participant that influences interactions without revealing itself. In the broader context of marine ecosystems, the frogfish represents an extreme example of how morphology and behavior can combine to create highly specialized survival strategies. Its ability to disappear in open view, to exist within the visual field of other organisms without being recognized, challenges the conventional understanding of camouflage. It demonstrates that invisibility is not always about blending in perfectly, but about being interpreted incorrectly. Through its sponge-like appearance, walking locomotion, and lure-based predation, the frogfish transforms the act of hunting into a process of controlled deception. It does not rely on speed or strength, but on the manipulation of perception, guiding the behavior of other organisms in ways that serve its needs. In this cluttered, complex environment, where every surface is occupied and every shape overlaps with another, the frogfish achieves a form of presence that is paradoxically defined by its absence. It is there, fully visible, interacting with its surroundings, yet unrecognized. And in that unrecognized state, it survives, feeds, and continues to shape the subtle dynamics of the reef, one unseen interaction at a time. Along the shadowed margins of coral reefs, where structure deepens into crevices and overhangs, the environment becomes less about open space and more about enclosed geometry. Cavities form between coral heads, tunnels run beneath collapsed rock, and narrow entrances open into chambers that remain hidden from the outside. Light struggles to penetrate these spaces, filtering in thin, fractured beams that illuminate only fragments of what lies within. In this layered architecture, visibility is limited not by distance, but by obstruction. What is seen is incomplete, and what is hidden often holds the greatest consequence. Within one such crevice, a head protrudes from darkness, motionless except for a slow, repetitive opening and closing of the jaws. The movement is steady, rhythmic and unmistakable. To an observer unfamiliar with the context, it appears aggressive, as though the animal is preparing to strike at any moment. The teeth, long and sharply curved, are fully exposed with each opening, reinforcing the impression of constant readiness. Yet this display, so often interpreted as a threat, is not what it seems. This is a moray eel, an animal whose behavior is frequently misunderstood because of how its physiology intersects with perception. The repeated opening and closing of the mouth is not an act of aggression, but a fundamental requirement for respiration. Unlike many fish that pump water across their gills by expanding and contracting the buccal cavity in more subtle ways, moray eels rely on this visible movement to draw water in and pass it over their gill structures. The act of breathing, in this case, mimics the visual cues of a predatory display. This creates a unique form of ecological misdirection. The eel appears constantly on the verge of attack, even when it is at rest. For potential predators, this may serve as a deterrent, signaling that the animal is alert and ready to defend itself. For prey, however, the interpretation is less straightforward. The continuous motion becomes normalized, part of the background behavior of the environment. What initially appears threatening becomes, over time, a constant that no longer triggers immediate avoidance. The body of the moray eel extends deep into the crevice, its elongated form coiled within the confines of the rock. Its skin, lacking the scales typical of many fish, is covered in a layer of mucus that reduces friction and protects against abrasion as it moves through tight spaces. The coloration varies by species, often matching the tones of the surrounding reef, with patterns that break up the outline of the body and blend with the textures of coral and rock. Positioning is critical. The eel does not patrol the reef in open water. Instead, it selects a location where its head can remain exposed while the rest of its body stays concealed. This arrangement provides both protection and strategic advantage. The narrow entrance of the crevice limits the directions from which the eel can be approached, reducing its vulnerability to larger predators. At the same time, it creates a controlled field of view, allowing the eel to monitor the movement of potential prey passing nearby. The sensory systems of the moray eel are adapted to this ambush lifestyle. Its vision, while functional, is not its primary tool for detecting prey. Instead, it relies heavily on olfaction, the ability to detect chemical cues in the water. Water flowing into the crevice carries with it traces of organisms in the surrounding area, allowing the eel to identify the presence of potential prey even when they are not directly visible. This chemical sensing provides a form of environmental awareness that extends beyond the limited visual field of the crevice. As a small fish moves along the reef face, its path brings it within range of the eel's position. The fish is aware of the crevices, of the potential dangers they may hold. But the constant presence of eels and other organisms within these spaces creates a complex landscape of risk assessment. Not every opening contains a predator, and not every predator is actively hunting. The fish must balance caution with the need to feed, to move, to exist within the reef. The eel's head remains still, its jaws continuing their rhythmic motion. To the fish, this behavior is familiar, part of the background activity of the reef. The opening and closing of the mouth does not change in response to the fish's presence. There is no sudden shift, no escalation that would signal immediate danger. The eel appears as it always does, breathing. This constancy is the foundation of the eel's strategy. By maintaining a behavior that is both necessary and misleading, it creates a scenario where its true intent is obscured. The prey does not perceive a change that would indicate a shift from rest to attack. Instead, it interprets the situation as stable, allowing it to move closer than it otherwise might. As the fish passes the entrance of the crevice, the eel's body remains coiled, its muscles poised for action. The strike, when it comes, is rapid and precise. The eel lunges forward, its jaws snapping shut around the prey with a force that leaves little opportunity for escape. The transition from stillness to motion is sudden, but the lack of preceding cues means the prey has no time to react. Once the prey is captured, the eel employs a second set of jaws located within its throat, known as pharyngeal jaws. These structures extend forward to grasp the prey and pull it deeper into the digestive tract, a mechanism that compensates for the eel's elongated body and limited ability to generate suction in the same way as other fish. This adaptation allows the eel to secure and process prey efficiently within the confined space of its crevice. The use of pharyngeal jaws represents a significant evolutionary innovation, one that enhances the eel's ability to exploit its ambush strategy. By separating the functions of capture and transport, the eel can maintain a firm grip on its prey, while ensuring that it is moved effectively into the digestive system. This dual jaw system is rare among vertebrates and highlights the specialized nature of the moray eel's feeding biology. The ecological role of the moray eel extends beyond its interactions with individual prey. As a mid-level predator, it influences the distribution and behavior of smaller fish and invertebrates within the reef. Its presence creates zones of risk around crevices and overhangs, areas that prey species must navigate with caution. This dynamic contributes to the overall complexity of the ecosystem, shaping patterns of movement and habitat use. At the same time, the eel itself is part of a larger network of interactions. It may be targeted by larger predators, particularly when it ventures out of its crevice to move between locations. In these moments, its elongated body and lack of rapid swimming capability can make it vulnerable. However, within its chosen habitat, its combination of camouflage, positioning, and deceptive signaling provides a high degree of security. The false aggression signal created by its breathing behavior illustrates a broader principle in animal communication and perception. Signals are often interpreted based on context and consistency. A behavior that is constant becomes part of the expected background, losing its ability to convey urgency. By aligning its necessary physiological function with a signal that appears threatening, the moray eel creates a paradox. It looks dangerous even when it is not acting aggressively, and as a result, its true moments of aggression are harder to detect. This misinterpretation is not absolute. Some species have evolved to recognize the risks associated with moray eels, maintaining greater distance or avoiding certain areas altogether. However, in a complex and densely populated reef, not all interactions can be governed by perfect information. The constant presence of multiple stimuli requires organisms to prioritize certain cues over others. And in this prioritization, opportunities arise for predators that can exploit the gaps. As the day progresses and light shifts across the reef, the interior of the crevice remains relatively unchanged. The eel continues its steady breathing, its presence a constant within the dynamic environment outside. Fish move in and out of view, currents carry particles through the water, and the reef continues its cycle of activity. Within this flow, the eel remains a fixed point, its strategy rooted in patience and precision. At times, the eel may leave its crevice, moving through the reef with a sinuous motion that allows it to navigate narrow spaces with ease. During these excursions, its behavior changes, becoming more active and exploratory. However, these movements are typically brief, and the eel returns to the security of its chosen position, where its ambush strategy is most effective. In the broader context of survival strategies, the moray eel represents a convergence of physiology and perception. Its breathing behavior, a necessity for its survival, doubles as a signal that influences how other organisms interpret its presence. Its positioning within the reef maximizes both protection and opportunity, allowing it to control interactions within a defined space. Through this combination of false aggression signals, ambush positioning, and specialized feeding mechanisms, the moray eel demonstrates that survival in complex ecosystems is not solely about physical capabilities, but about how those capabilities are perceived by others. It does not hide completely, nor does it actively pursue its prey. Instead, it exists in a state of apparent readiness, its true intent masked by the very behavior that keeps it alive. In the dim, structured world of the reef's hidden spaces, where visibility is partial and interpretation is uncertain, the pitcher set. Moray eel turns a simple act, breathing, into a tool of deception. And in doing so, it reveals that sometimes the most effective way to hunt is not to conceal aggression, but to display it so constantly that it loses its meaning, leaving only the moment when it matters most. The coastal waters shift character as the reef gives way to open shallows, where sandy bottoms stretch outward and sunlight penetrates with almost uninterrupted intensity. Here the water appears deceptively simple, a clear column of blue-green light where objects should be easy to detect and movement should stand out against the uniform background. Yet this apparent clarity creates a different kind of challenge. In an environment where there is little structure to hide behind, survival depends not on blending into complexity, but on reducing presence to the point where detection fails entirely. Suspended within this illuminated space, something moves that is almost impossible to see. There is no solid outline, no defined coloration, no shadow that anchors it to a particular location. Only a faint distortion of light hints at its existence, a slight bending of the visual field that shifts as it changes position. This is the box jellyfish, an organism that has evolved to approach invisibility not through mimicry or disguise, but through the absence of visual information. Its body, known as the bell, is composed of a gelatinous matrix that is nearly transparent. Light passes through it with minimal scattering, allowing it to blend seamlessly with the surrounding water. Unlike many organisms that rely on pigmentation to match their environment, the box jellyfish eliminates the need for color entirely. It becomes a medium through which light travels, rather than a surface that reflects it. Extending from the corners of the bell are long, delicate tentacles, each one lined with specialized cells called nematocysts. These cells contain microscopic harpoons loaded with venom, capable of firing upon contact with remarkable speed. The tentacles themselves are almost invisible, thin and translucent, trailing behind the bell in the water. In certain lighting conditions, they can only be detected by the faintest glimmer or the way they slightly alter the movement of particles in the water. This combination of transparency and fine structure creates a predator that is effectively absent from the visual field of its prey. Small fish and planktonic organisms move through the water, navigating by light gradients and the detection of more substantial objects. The box jellyfish does not present the cues that would trigger avoidance. It does not cast a strong shadow. It does not reflect light in a way that distinguishes it from the background. It is present, but not perceived. Unlike many jellyfish which drift passively with currents, the box jellyfish exhibits a level of active movement that sets it apart. Its bell contracts rhythmically, propelling it through the water with a degree of control that allows for directional movement. This ability to swim, rather than simply drift, enables it to position itself within areas of higher prey density, increasing the likelihood of encounters. The control of movement is complemented by a surprisingly advanced sensory system. The box jellyfish possesses clusters of simple eyes, known as rhopalia, which are capable of detecting light intensity and direction. Some of these eyes include lens structures that allow for image formation, a rare feature among jellyfish. While not comparable to the vision of more complex animals, this system provides enough information for the jellyfish to navigate its environment, avoiding obstacles and orienting itself relative to the surface. As it moves through the water, the box jellyfish adjusts its position in response to subtle changes in light and current. It may ascend toward brighter regions during certain times of day, or descend slightly to maintain optimal conditions for hunting. This vertical movement is not random. It reflects an interaction between the organism's sensory capabilities and the distribution of prey within the water column. A small fish swims through the shallows, its body catching the sunlight as it moves. It is alert to larger shapes, to sudden changes in movement, to the shadows that might indicate a predator. The water around it appears empty, a clear space through which it can move freely. Yet within this space, The tentacles of the box jellyfish extend silently, forming a nearly invisible barrier. The fish continues its path, unaware of the danger ahead. There is no signal to trigger an escape response, no visual cue that indicates the presence of a threat. The tentacles, though present, do not disrupt the water in a way that the fish can detect. They simply exist, suspended in the same medium, indistinguishable from it. Contact is instantaneous and decisive. As the fish brushes against a tentacle, the nematocysts fire, embedding their microscopic harpoons into the tissue. Venom is delivered rapidly, interfering with cellular function and neural activity. The fish's movement becomes erratic, its ability to coordinate disrupted within moments. The jellyfish responds by adjusting its position, bringing the bell and additional tentacles into contact with the immobilized prey. The process of envenomation is not merely a defensive mechanism. It is a primary means of capturing and subduing prey. The venom of the box jellyfish is among the most potent in the marine environment, capable of affecting a wide range of organisms. Its effectiveness lies in both its surah of delivery and its biochemical composition, which targets multiple physiological systems simultaneously. Once the prey is subdued, the jellyfish uses its tentacles to guide it toward the mouth, located at the center of the bell's underside. The feeding process is slow compared to the initial capture, as the organism digests its prey externally before absorbing the nutrients. Throughout this process, the jellyfish maintains its position within the water column, its transparency continuing to shield it from detection by other organisms. The ecological role of the box jellyfish extends beyond individual predation events. As an active hunter in the planktonic environment, it influences the distribution and behavior of smaller organisms, contributing to the dynamic balance of the ecosystem. Its presence creates zones of risk that are not easily defined by visual cues, adding a layer of unpredictability to the interactions within the water column. At the same time, the box jellyfish itself is part of a larger network of interactions. Certain predators, including some species of fish and turtles, have developed resistance to its venom and may prey upon it. However, the effectiveness of its transparency and the potency of its defense mechanisms reduce the frequency of such encounters, allowing it to occupy a relatively secure position within its ecological niche. The concept of invisibility in this context is not absolute. Under certain lighting conditions, the box jellyfish can be detected by careful observation, its outline revealed by slight distortions in the water or by the way light refracts through its body. However, for the majority of organisms within its environment, these cues are insufficient to trigger recognition. The threshold for detection is not reached, and the jellyfish remains effectively unseen. This strategy highlights a fundamental aspect of perception in aquatic environments. Detection is not solely about the presence of an object, but about the contrast between that object and its surroundings. By minimizing this contrast to near zero, the box jellyfish removes itself from the sensory framework of other organisms. It does not hide behind structures or mimic specific forms. It simply reduces its visibility to the point where it is no longer processed as a distinct entity. As the day progresses and the angle of sunlight changes, the appearance of the water column shifts subtly. Reflections from the surface create patterns of light that move across the water, further complicating the visual environment. The box jellyfish continues its movement within this shifting field, its transparency adapting naturally to the changing conditions without the need for active adjustment. In the late afternoon, as the intensity of light decreases, the dynamics of the ecosystem begin to change. Some prey species move closer to the surface, taking advantage of reduced visibility to feed. The box jellyfish responds by adjusting its position, maintaining proximity to these movements while preserving its advantage of invisibility. In this environment, where clarity does not guarantee safety, the box jellyfish represents a different approach to survival. It does not rely on speed, strength, or complex behavioral strategies. Instead, it removes itself from the perceptual landscape, becoming a presence that exists without being acknowledged. Through its transparent body, nearly invisible tentacles, and active movement, it transforms the open water into a space where danger is not marked by obvious signs, but by the absence of them. Prey does not flee because it does not know there is anything to flee from. And in that absence of recognition, the box jellyfish thrives, an unseen force moving through the light, shaping the lives of other organisms without ever announcing its own. Across the reef's quieter zones, where coral growth gives way to mixed terrain of rubble, sand, and scattered biological debris, the environment becomes a collage of textures layered without clear boundaries. Broken coral branches lie partially buried, sponges expand into uneven shapes, algae coat surfaces in soft, irregular patches, and fragments of shells accumulate in pockets shaped by currents. It is not a place of visual clarity, but of excess information. Every surface is already occupied by patterns, colors, and forms that overlap and obscure one another. In such a landscape, recognition is not simply difficult. It is unreliable. Moving slowly across this fragmented terrain, something advances that does not appear to be a single organism at all. At first glance, it resembles a loose cluster of algae-covered debris, a small drifting island of organic material shifting slightly with the movement of water. Pieces of sponge, bits of plant matter, and fragments of shell seem to cling together in an arrangement that lacks symmetry or intention. Yet this apparent randomness is, in fact, highly controlled. Beneath this assembled exterior is a crab, one that has transformed its own body into a platform for disguise. Unlike animals that rely solely on internal coloration or structural mimicry, this crab employs an external strategy. It collects materials from its environment and attaches them to its carapace, effectively constructing a living camouflage that mirrors the surrounding habitat with remarkable accuracy. Small hooks and specialized setae on its shell allow it to anchor pieces of algae, sponge, and other organisms securely in place. Over time, these materials may even continue to grow, further integrating the crab into the biological fabric of the reef. This process of decoration is not random gathering. The crab selects materials based on availability and effectiveness, often favoring organisms that are common in its immediate environment. In areas dominated by algae, it will incorporate more plant matter. In sponge-rich zones, it may attach pieces of sponge that match the local color and texture. This selective behavior suggests a level of environmental assessment, where the crab aligns its disguise with the dominant visual cues of its surroundings. As it moves, the illusion persists. The crab does not reveal itself through typical locomotion patterns. Its legs move in a coordinated sideways motion characteristic of crabs, but the attached materials disrupt the visibility of this movement. The appendages become obscured by the layered decoration, their motion softened and fragmented by the shifting mass above them. To an observer, the entire structure appears to drift or shift rather than walk, its movement blending with the subtle displacement of debris caused by currents. This ability to hide while moving is a critical extension of its strategy. Many forms of camouflage fail when the organism changes position, as movement introduces cues that break the illusion. The decorating crab mitigates this by ensuring that its entire external profile remains consistent with the environment, even during locomotion. The materials it carries move with it, maintaining the same textures and colors regardless of position. In this way, the crab does not step out of its disguise. It carries the environment with it. A small fish navigates the rubble field, its attention divided between feeding and avoiding more obvious threats. It passes near the crab, its sensory systems scanning for recognizable shapes and movements. The cluster of algae and sponge does not register as a potential predator. It is part of the background, one of many similar structures scattered across the seafloor. The fish adjusts its path slightly to avoid collision, but does not flee or investigate further. The crab continues its movement, undetected, its disguise functioning not by hiding in place, but by redefining what it is perceived to be. It is no longer categorized as an animal, but as an extension of the environment. This misclassification is more effective than simple concealment because it bypasses the recognition process entirely. The observer does not fail to see the crab. It fails to interpret it as something worth attention. This strategy provides advantages in both defense and predation. As a potential prey item, the crab reduces its visibility to predators, many of which rely on visual cues to identify targets. The irregular shape and texture of its decoration disrupt the outlines that predators use to detect and track movement. Even if a predator's gaze passes over the crab, the lack of a clear, recognizable form reduces the likelihood of an attack. At the same time, the crab can use its disguise to approach food sources without triggering avoidance behaviors. Small invertebrates and organic matter within the rubble field become accessible as the crab moves through the environment. Its feeding behavior is subtle, involving the use of specialized mouthparts to process detritus, algae, or small organisms. The act of feeding does not require large, conspicuous movements, allowing the crab to maintain its disguise even while actively interacting with its surroundings. The biological mechanisms that support this strategy extend beyond the physical attachment of materials. The crab's exoskeleton provides a stable platform for decoration, but it must also accommodate growth and molting. As the crab grows, it sheds its old exoskeleton and forms a new one, a process that temporarily leaves it vulnerable. During this period, it must reconstruct its camouflage, collecting new materials and re-establishing its disguise. This cycle introduces a dynamic element to its otherwise stable strategy, requiring periodic investment in rebuilding its protective exterior. The relationship between the crab and the organisms it uses for decoration can also be complex. In some cases, the attached materials are living organisms that continue to grow and function while on the crab's shell. This creates a form of incidental symbiosis, where the organisms gain mobility and access to new areas, while the crab benefits from their presence as camouflage. The exact nature of these interactions varies, but they illustrate the interconnectedness of the reef ecosystem, where even a single strategy can involve multiple species. As currents shift and particles move through the water, the crab adjusts its position, navigating the terrain with careful, deliberate steps. Its movement is not random, but guided by the structure of the environment and the distribution of resources. It may seek out areas with higher concentrations of food or more effective materials for decoration, balancing the need for sustenance with the maintenance of its disguise. In areas where the environment changes, such as transitions between algae-dominated zones and coral rubble, the effectiveness of the crab's camouflage may vary. In such cases, the crab may alter its decoration over time, replacing materials that no longer match the surroundings. This gradual adaptation allows it to maintain alignment with the environment, even as conditions shift. The sensory world of the crab supports this behavior. Its eyes, positioned on stalks, provide a wide field of view, allowing it to monitor its surroundings without moving its body. Its antennae and other sensory structures detect chemical and mechanical cues in the water, informing it of changes in the environment and the presence of other organisms. These inputs guide its decisions, from where to move to what materials to collect. Predators that rely on other sensory modalities, such as smell or vibration, may still detect the crab despite its visual disguise. However, the combination of reduced visual recognition and the masking effects of the attached materials can still provide a significant advantage, particularly in environments where visual cues dominate. As the day progresses and light conditions change, the appearance of the rubble field shifts. Shadows deepen, colors become more muted, and the overall contrast of the environment decreases. The crab's decoration continues to match these conditions, its effectiveness maintained by the inherent variability of the materials it carries. The irregularity of its appearance allows it to blend across a range of lighting conditions, reducing the need for precise alignment with a single visual state. In the broader context of marine camouflage, the decorating crab represents a unique approach, one that extends beyond internal adaptation into the manipulation of external elements. It does not rely solely on its own biology to achieve concealment. Instead, it incorporates the environment directly into its body, creating a hybrid form that is part organism, part habitat. This strategy highlights a different dimension of survival, one where the boundary between the individual and the environment becomes blurred. The crab is not separate from its surroundings. It carries them, integrates them, and becomes them in a way that challenges the distinction between organism and context. As the reef settles into the quieter rhythms of evening, the crab continues its slow movement across the seafloor, its presence unremarked by the many organisms around it. It feeds, it navigates, it persists, all while remaining within the field of view, yet outside the realm of recognition. Through disguise and decoration, it demonstrates that invisibility does not always require hiding or transforming internally. Sometimes, it is achieved by adopting the world itself, by wearing the environment so completely that the question of identity never arises. In this subtle merging of form and context, the crab reveals a strategy that is both simple and profound, one that turns the complexity of the reef into a shield and movement itself into a continuation of the landscape. In the shifting margins between reef and open water, where coral structures loosen into sandy channels and scattered outcrops, the environment becomes a place of exposure balanced by brief moments of cover. Visibility is high, currents are unpredictable, and the distance between safety and vulnerability can be measured in seconds. In this transitional zone, many organisms rely on speed to escape danger, darting between coral heads or vanishing into narrow crevices. But not all creatures are built for speed, and some have evolved a strategy that does not depend on fleeing at all. Instead, they alter the very perception of their presence, transforming themselves in an instant from vulnerable prey into something far more difficult to interpret. A pufferfish moves cautiously along the sandy bottom, its body compact and unassuming, its fins beating in short, controlled bursts that keep it hovering just above the substrate. In this state, it appears relatively ordinary, its coloration blending with the muted tones of the environment, its movement neither particularly fast nor particularly slow. It feeds intermittently, using its strong beak-like jaws to crush small invertebrates hidden within the sand or attached to fragments of coral. There is nothing about its initial appearance that suggests the dramatic transformation it is capable of. Yet beneath this calm exterior lies a physiological system designed for rapid and extreme change. The pufferfish's body is structured with highly elastic skin and a specialized internal anatomy that allows it to take in large volumes of water in a very short time. Its stomach, normally compact, can expand dramatically, accommodating this sudden intake and redistributing the water throughout the body cavity. This expansion is not gradual. It is explosive, a transformation that can occur in moments when triggered by the presence of a threat. The trigger itself is often subtle, a shift in water pressure, a sudden movement in the periphery, or the approach of a predator whose intent becomes clear only at close range. In this exposed environment, hesitation can be fatal, and the pufferfish's response is designed to eliminate hesitation entirely. When the threshold is crossed, the transformation begins. The fish opens its mouth wide, drawing in water with rapid, forceful gulps. Its body begins to swell, the skin stretching outward as the internal volume increases. The change is immediate and dramatic. What was once a small, streamlined fish becomes a rounded, inflated form that bears little resemblance to its original shape. At the same time, small spines embedded within the skin, previously lying flat, begin to erect, extending outward as the body expands. This combination of inflation and spine erection alters the fish's silhouette completely. The smooth, compact outline is replaced by a larger, more irregular form, one that presents a far more challenging target for any predator. The increase in size alone can be enough to deter certain attackers, particularly those whose feeding strategies depend on swallowing prey whole. A predator that could easily consume the pufferfish in its normal state may find the inflated version physically impossible to ingest. But the transformation is not solely about physical limitation. It is also a visual signal, one that communicates a sudden shift in risk. The rapid change in size and shape creates a moment of confusion, a disruption in the predator's perception that forces it to reassess the situation. The prey it was pursuing is no longer the same object. Its dimensions, its texture, and its overall appearance have changed in an instant, breaking the continuity of the attack sequence. A predatory fish approaches, its body streamlined for speed, its eyes focused on the pufferfish as a potential meal. In the initial moments, the pufferfish presents a familiar target, one that fits within the predator's expectations of size and behavior. The predator accelerates, closing the distance with the intention of capturing its prey before it can escape. Then the transformation occurs. The pufferfish inflates, its body expanding outward, its spines erecting in all directions. The predator, mid-approach, is confronted with a completely different object than the one it had targeted. The change is so abrupt that it interrupts the predator's attack sequence, introducing uncertainty at the critical moment. The predator slows, its forward momentum reduced as it attempts to process the new information. This hesitation is the pufferfish's advantage. In predator-prey interactions, timing is crucial, and any disruption in the sequence of attack can provide an opportunity for the prey to survive. By altering its size and shape so dramatically, the pufferfish forces the predator to re-evaluate its decision, often resulting in the abandonment of the attack. The erected spines add another layer to this defense. While not all pufferfish species possess highly pronounced spines, those that do create a surface that is not only larger, but also more difficult to grasp or bite. The spines can interfere with the predator's ability to secure a hold, increasing the risk of injury or failure during the attack. Combined with the increased size, this makes the inflated pufferfish a far less appealing target. Beyond the mechanical aspects of inflation, there is a chemical dimension to the pufferfish's defense. Many species contain potent toxins within their tissues, particularly in the liver, skin, and other organs. These toxins can be harmful or even lethal if ingested, providing an additional deterrent to predators. While the inflation itself does not directly deploy these toxins, the visual display may serve as a warning, signaling that the fish is not only difficult to consume, but potentially dangerous. The effectiveness of this strategy depends on the predator's ability to recognize and respond to these cues. In ecosystems where pufferfish are common, predators may learn to associate the inflated form with negative outcomes, avoiding them altogether. In areas where such encounters are less frequent, the initial confusion created by the transformation may be sufficient to prevent a successful attack. Once the immediate threat has passed, the pufferfish must reverse the process, expelling the water it has taken in and returning to its normal size. This deflation is more gradual than the inflation, as the fish releases water through its gills and mouth, reducing its volume and allowing the skin to return to its original state. During this period, the fish may remain relatively stationary, conserving energy as it recovers from the exertion of the transformation. The energetic cost of inflation is significant, and the pufferfish does not use this defense lightly. It is reserved for situations where the risk of predation is high and other options such as escape or concealment are not viable. This selective use reflects a balance between the benefits of the defense and the costs associated with deploying it. In the broader ecological context, the pufferfish occupies a role that is shaped by both its feeding habits and its defensive capabilities. As a consumer of hard-shelled invertebrates, it contributes to the regulation of populations that might otherwise dominate certain areas of the reef. Its strong jaws allow it to access food resources that are unavailable to many other species, giving it a niche within the ecosystem. At the same time, its presence influences the behavior of predators, which must account for the possibility of encountering a prey item that can rapidly become difficult or dangerous to consume. This dynamic adds a layer of complexity to the interactions within the reef, where decisions are not based solely on immediate opportunity, but on the potential consequences of engaging with certain species. The sensory systems of the pufferfish support its ability to detect and respond to threats. Its vision allows it to monitor its surroundings, while its lateral line system detects changes in water movement, providing early warning of approaching predators. These inputs are integrated to determine when to initiate the inflation response, ensuring that it is used at the appropriate moment. As the day progresses and light conditions change, the pufferfish continues its routine, feeding and moving through the transitional zone. Its appearance remains unremarkable, its presence blending into the background of the environment. It does not advertise its defensive capabilities, nor does it rely on them for every interaction. Instead, it exists within the system as a potential, a latent transformation that can be activated when necessary. In this environment, where exposure is constant and the margin for error is small, the pufferfish demonstrates a different approach to survival. It does not rely on speed or concealment alone. It relies on the ability to alter perception, to become something else at the critical moment, reshaping the interaction between predator and prey. Through the illusion of size, the rapid inflation of its body, and the erection of its spines, it transforms itself from a manageable target into a complex and uncertain object. In doing so, it introduces hesitation, confusion, and ultimately, a chance to survive in a world where clarity often determines fate. In the upper layers of tropical coastal waters, where sunlight penetrates deeply and the ocean becomes a field of moving light rather than a fixed landscape, the rules of perception begin to shift. Here, visibility is not simply about clarity, but about distortion. Sunbeams fracture as they pass through rippling surfaces, scattering into shifting patterns that dance across the bodies of fish and the open water around them. The environment is not static. It flickers, pulses, and refracts, turning every movement into a visual echo. In this space, where light is constantly bending and breaking, the ability to remain unseen does not depend solely on hiding. It depends on becoming part of the distortion itself. A barracuda patrols this luminous corridor, its body long and narrow, suspended in near-perfect stillness between bursts of motion. At first glance, it appears almost too visible, its form outlined clearly against the blue water, its presence defined by sharp angles and metallic sheen. It does not hug the reef or seek cover among structures. Instead, it occupies open space, where there is little to obscure it and nowhere to hide in the conventional sense. Yet despite this apparent exposure, it is rarely detected until it chooses to be. The key to this paradox lies in the surface of its body. The barracuda's scales are not merely protective, they are highly reflective, arranged in a way that interacts with incoming light to produce a constantly shifting pattern of brightness and shadow. Each scale acts as a small mirror, catching sunlight and redirecting it in slightly different directions. As the fish moves, even subtly, these reflections change, creating a dynamic visual effect that disrupts the perception of its true shape and position. In an environment where light is already fragmented by the movement of water, these reflections blend seamlessly with the background. The barracuda does not stand out as a solid object. Instead, it appears as a series of glints and flashes, indistinguishable from the surrounding play of light. To an observer, its outline becomes difficult to fix, its edges dissolving into the shifting patterns around it. This effect is particularly powerful when viewed from below. Prey fish looking upward into the brighter surface layers are already challenged by glare and contrast. The barracuda's reflective body amplifies this challenge, scattering light in ways that obscure its approach. The fish does not appear as a coherent predator moving toward them, but as a series of transient highlights that flicker and vanish within the broader field of illumination. The sensory systems of these prey fish are adapted to detect motion and contrast, to identify threats based on changes in the environment. However, when the environment itself is in constant motion, and when the predator's appearance mimics that motion, detection becomes unreliable. The barracuda exploits this limitation, positioning itself within the visual noise of the water column. A school of smaller fish moves through this space, their bodies reflecting light in their own way, creating a collective shimmer that both protects and exposes them. Schooling behavior relies on coordination and the dilution of risk, making it more difficult for a predator to isolate a single target. But this strategy depends on the ability to detect and respond to threats in time. If the threat cannot be clearly identified, the cohesion of the group becomes a vulnerability rather than a defense. The barracuda adjusts its position with minimal movement, aligning itself with the direction of the light and the motion of the water. Its body remains rigid, its fins making only slight corrections to maintain orientation. In this state, it is not actively pursuing its prey. It is waiting, allowing the environment to conceal its presence. The concept of light distortion here is not passive. It is actively used as a tool. The barracuda's reflective scales do not simply mirror the surroundings. They interact with the angle of the sun, the movement of the surface, and the position of the observer to create a shifting illusion. This illusion breaks the continuity of its form, making it difficult for prey to track its direction or speed. As the school of fish approaches, the barracuda remains within this distorted field, its presence masked by the interplay of light. The prey fish continue their movement, their attention focused on maintaining formation and avoiding more obvious threats. The subtle distortions around them do not trigger a response, as they fall within the range of normal environmental variation. At a critical moment, the barracuda transitions from stillness to motion. This change is instantaneous, a rapid acceleration driven by powerful muscle contractions along its body. The elongated form that was previously difficult to define becomes a focused line of movement, cutting through the water with precision. The suddenness of this attack is a direct extension of the preceding illusion. Because the prey could not track the barracuda's position accurately, they are unprepared for the speed and direction of the strike. The transition from invisibility to impact is so abrupt that there is little time for escape. The barracuda's jaws, equipped with sharp interlocking teeth, close around its target with force, securing the prey before it can react. The attack is not prolonged. It is a single, decisive action that relies on the element of surprise created by the preceding visual distortion. After the strike, the barracuda may continue its movement briefly before slowing and returning to a more neutral state. The reflective scales once again blend with the environment, the sharp outline dissolving back into the shifting light. The predator becomes once more a part of the visual field rather than a distinct object within it. This cycle of concealment and sudden action defines the barracuda's role within this ecosystem. It does not rely on complex structures or elaborate camouflage patterns. Instead, it uses the properties of light itself, turning the dynamic nature of its environment into an extension of its body. The biological adaptations that support this strategy extend beyond the scales. The barracuda's streamlined shape reduces drag, allowing for rapid acceleration and efficient movement through the water. Its musculature is adapted for bursts of speed, providing the alcua needed to close the distance between predator and prey in a fraction of a second. Its eyes are positioned to provide forward vision, allowing it to focus on targets during the final phase of the attack. The integration of visual input with muscular response is critical, as the success of the strike depends on precise timing and alignment. At the same time, the barracuda must manage its own visibility to other predators. While it is an effective hunter, it is not immune to predation, particularly when it is young. The same reflective properties that help it hunt can also make it more difficult to detect by larger predators, especially in the complex lighting conditions of the upper water column. The interplay between predator and prey in this environment is shaped by the physics of light, as much as by the biology of the organisms involved. Refraction, reflection, and absorption all influence how objects are perceived, creating a dynamic visual landscape where certainty is rare. In this context, the barracuda's strategy can be understood as an exploitation of sensory limitations. It does not hide in the traditional sense, nor does it mimic a specific object. Instead, it becomes part of the visual noise, a distortion that blends with other distortions until it is indistinguishable from them. As the sun moves across the sky, the angle and intensity of light change, altering the patterns within the water. The barracuda adjusts its position accordingly, maintaining its alignment with the prevailing conditions. This adaptability ensures that its reflective camouflage remains effective throughout the day. In moments when the water surface is calm, the patterns of light may become more stable, reducing the level of distortion. In such conditions, the barracuda may rely more on its ability to remain still and on the contrast between its reflective body and the background. When the surface is disturbed and light patterns become more chaotic, the effectiveness of its mirror-like scales increases, providing greater concealment. The relationship between environmental conditions and predatory success is not static. It varies with time, weather, and location, requiring the barracuda to continuously adjust its behavior. This flexibility is a key component of its survival strategy, allowing it to operate effectively across a range of conditions. As the day fades and the intensity of light diminishes, the visual dynamics of the water change once again. The bright reflections give way to softer tones, and the contrast between objects decreases. In these conditions, the barracuda's reflective scales may be less prominent, but its ability to blend with the environment remains, supported by its coloration and behavior. In the broader ecological network, the barracuda serves as a regulator of fish populations, influencing the distribution and behavior of its prey. Its presence affects how schools move, where they feed, and how they respond to perceived threats. This influence extends beyond individual interactions, shaping the dynamics of the ecosystem as a whole. Through the use of mirror-like reflection, light distortion, and sudden, precise attacks, the barracuda demonstrates a strategy that is both simple and sophisticated. It does not overpower its prey through brute force alone, nor does it rely on complete invisibility. Instead, it operates within the margins of perception, where visibility and invisibility are not fixed states, but fluid conditions shaped by light and movement. In this constantly shifting environment, the barracuda's greatest advantage is not just its speed or its teeth, but its ability to remain undefined until the moment of action. By the time its presence becomes clear, the outcome is already decided, and the illusion of safety that once surrounded its prey has been irreversibly broken. In the open water beyond the structural complexity of reefs, where the seafloor drops away and the ocean becomes a vast, three-dimensional expanse, vision begins to lose its dominance. Light still penetrates, but it is filtered, scattered, and absorbed as depth increases, turning the environment into gradients of blue and shadow rather than sharply defined forms. In this space, distance is deceptive, movement is harder to interpret, and objects can appear and disappear depending on angle and light. For many species, survival depends on what can be seen. For others, it depends on what cannot. A group of dolphins moves through this open water with fluid precision, their bodies streamlined and their movements coordinated in a way that suggests a shared awareness of the environment. They do not rely solely on sight to navigate this space. Instead, they operate within a sensory world that extends far beyond the visible spectrum, using sound as a primary tool to perceive, interpret, and ultimately manipulate their surroundings. Each dolphin produces a series of rapid, high-frequency clicks, emitted through specialized structures in its head. These clicks travel through the water as focused beams of sound, spreading outward until they encounter objects in their path. When these sound waves strike a surface, whether it is the body of a fish, a patch of plankton, or the seafloor far below, they reflect back toward the source. The returning echoes are received through the dolphin's lower jaw and transmitted to the inner ear, where they are processed into detailed spatial information. This process, known as echolocation, allows dolphins to construct a mental map of their environment with remarkable accuracy. They can determine the size, shape, distance, and even the internal structure of objects based on the characteristics of the returning echoes. In this sense, they do not simply detect the presence of prey. They perceive it in a way that integrates both external form and internal composition, revealing details that are invisible to the eye. In the open water, a school of fish moves as a cohesive unit, its members maintaining close proximity to one another in a constantly shifting formation. This schooling behavior is a defense mechanism, reducing the likelihood that any single individual will be targeted by a predator. The collective movement creates a dynamic pattern that can confuse attackers, making it difficult to isolate a specific target. However, this strategy is built on the assumption that the predator relies on visual cues to track and select prey. Against a predator that uses sound as its primary sensory modality, the effectiveness of this defense begins to diminish. The dense cluster of fish reflects echolocation clicks as a single complex object, but within that object, individual fish can still be distinguished based on subtle differences in echo patterns. The dolphins approach the school from multiple directions, their movements coordinated through both visual signals and acoustic communication. They do not rush in immediately. Instead, they begin by mapping the structure of the school, using echolocation to assess its density, shape, and movement patterns. This initial phase is not about capture, but about understanding. As the dolphins emit their clicks, the sound waves interact with the tightly packed bodies of the fish, creating a cascade of echoes that overlap and interfere with one another. This acoustic environment becomes increasingly complex, not only for the dolphins, but also for the fish. While fish do not use echolocation in the same way, they possess sensory systems that can detect vibrations and pressure changes in the water, such as the lateral line system. The influx of acoustic energy from the dolphins can disrupt these systems, creating a form of sensory noise that interferes with the fish's ability to coordinate their movements. This is where the concept of acoustic illusion begins to take shape. The dolphins are not merely observing the school. They are actively altering the sensory environment in which the fish operate. By emitting coordinated bursts of sound, they create a field of interference that can confuse the fish, disrupting the signals that maintain the integrity of the school. The fish begin to lose cohesion, their synchronized movements breaking down as individuals struggle to interpret the conflicting sensory inputs. The tight formation loosens, gaps appear, and the once unified structure becomes fragmented. This fragmentation is the critical moment, the point at which the defensive advantage of the school is compromised. The dolphins respond immediately, transitioning from mapping to active hunting. They move in coordinated patterns, each individual taking a position that contributes to the overall strategy. Some dolphins may circle the school, using their bodies and movements to contain it within a defined area. Others may drive the fish upward toward the surface, where escape options are limited. In some cases, dolphins are known to create rings of bubbles, a behavior that further confines the fish and enhances the acoustic effects of their clicks. Within this controlled environment, the dolphins use echolocation not only to detect prey, but to track individual fish with precision. The returning echoes provide continuous feedback, allowing them to adjust their movements in real time. The prey, meanwhile, is operating in a degraded sensory state, its ability to respond effectively reduced by the acoustic disturbance. One of the most striking aspects of this interaction is the dolphin's ability to coordinate their actions without relying on constant visual contact. Their communication extends into the acoustic domain, where whistles and clicks can convey information about position, intent, and timing. This shared acoustic space allows the group to function as a cohesive unit, each individual contributing to the success of the hunt. The concept of invisible sensing becomes evident in this process. The dolphins are perceiving and interacting with their environment in ways that are not apparent to an external observer. Their understanding of the space around them is constructed through sound, creating a layer of perception that exists alongside, but independent of, the visible world. As the hunt intensifies, the dolphins exploit the confusion within the school. They make rapid, targeted movements, selecting individual fish based on the information provided by their echolocation. Each capture is a brief, precise action, the culmination of a complex sequence of sensory processing and coordinated behavior. The fish, once protected by the collective structure of the school, are now exposed as individuals. Their attempts to reform the school are hindered by the ongoing acoustic disturbance, which continues to disrupt their coordination. The very mechanism that once ensured their safety has been turned against them, transformed into a liability by the dolphins' manipulation of the sensory environment. The biological adaptations that enable this strategy are the result of a long evolutionary process. The dolphin's auditory system is highly specialized, capable of detecting and interpreting a wide range of frequencies with exceptional sensitivity. The structures involved in sound production and reception are finely tuned, allowing for the precise control and analysis of echolocation signals. At the same time, the cognitive abilities of dolphins play a crucial role. Their capacity for learning, memory, and problem-solving allows them to develop and refine complex hunting strategies. The coordination observed in group hunting is not merely instinctual. It reflects a level of social organization and communication that supports cooperative behavior. This cooperation extends beyond immediate hunting scenarios. Dolphins are known to share information within their groups, potentially passing on successful strategies to other members. This cultural transmission adds another layer to their behavior, allowing for the accumulation of knowledge over time. In the broader ecological context, the presence of dolphins influences the behavior and distribution of prey species. Fish may alter their schooling patterns, movement routes, or habitat use in response to the threat posed by these predators. This dynamic interaction shapes the structure of the ecosystem, creating a balance between predator and prey that is constantly evolving. As the hunt concludes, the dolphins gradually reduce their acoustic activity, the intensity of their clicks diminishing as the need for active manipulation of the environment decreases. The remaining fish begin to regroup, their sensory systems recovering from the disturbance, the school slowly reforming into a cohesive unit. The dolphins move on, their bodies once again gliding through the open water with apparent ease. The environment returns to its baseline state, the visible patterns of light and movement continuing as before. Yet beneath this surface, the acoustic landscape remains a fundamental aspect of how this ecosystem functions. Through the use of echolocation, coordinated behavior, and the deliberate creation of acoustic illusions, dolphins demonstrate a form of predation that operates beyond the limits of vision. They do not simply chase or ambush their prey. They reshape the sensory world in which the prey exists, turning perception itself into a tool of control. In this vast, open environment, where sight can be deceived by light and distance, the dolphins reveal a deeper layer of interaction, one where sound defines reality, and where the unseen becomes the decisive factor in survival. In the wide, open corridors of tropical seas, where currents stretch across vast distances and the seafloor falls away into blue depth, the environment becomes defined less by structure and more by movement. Here, life is carried rather than anchored. Microscopic plankton drift in invisible highways, following temperature gradients, nutrient flows, and the slow pulse of ocean circulation. These drifting organisms form the foundation of an entire food web, yet they are too small to be seen individually. Instead, their presence is revealed only in density, in the faint clouding of water, in the subtle change of color that marks a feeding ground for animals that have learned to read what cannot be directly observed. In this open expanse, where there are no rocks to hide behind and no coral to blend into, the concept of camouflage seems almost irrelevant. There is nowhere to disappear. Yet even here, concealment exists, not as a matter of blending into the environment, but as a matter of being misinterpreted within it. Movement, shape, and light become the tools of illusion, and few animals demonstrate this more effectively than the manta ray. A large shadow passes just beneath the surface, its edges soft and shifting, its movement so smooth that it barely disturbs the water around it. At first, it does not appear as an animal at all. It resembles a passing cloud, a transient darkening of the light field caused by something distant or undefined. Its body is broad and flattened, extending outward into wing-like pectoral fins that span several meters across. This size, rather than making it more obvious, contributes to the illusion. The larger the form, the more it blends into the general play of light and shadow that characterizes the open ocean. The manta ray does not swim in the conventional sense. It glides. Its movements are slow, deliberate, and continuous, driven by gentle undulations of its fins that push against the water with minimal turbulence. This style of locomotion is highly efficient, allowing the manta to travel long distances without expending large amounts of energy. But it also has another effect. It reduces the visual cues that typically signal the presence of a large moving organism. Most fish, when they swim, generate a series of rapid, oscillating movements that create clear patterns in the water. These patterns are detected by both visual systems and mechanosensory systems, such as the lateral line, alerting nearby animals to their presence. The manta ray, by contrast, produces a movement that is closer to drifting than to swimming. Its large fins move slowly, displacing water in a way that lacks sharp changes or sudden accelerations. The result is a motion that blends with the natural flow of currents, making it difficult to distinguish from the background dynamics of the ocean. This is the foundation of the shadow illusion. The manta ray's body blocks light from above, casting a broad, diffuse shadow beneath it. But because the edges of this shadow are not sharply defined, and because the movement of the manta is so smooth, the shadow does not immediately register as a threat. It becomes part of the ambient variation in light, one of many shifting patterns that play across the water column. Below, small fish and planktonic organisms drift and feed, their attention focused on the immediate tasks of survival. For many of these organisms, detection of predators relies on recognizing specific shapes, movements, or contrasts. A fast-approaching silhouette, a sudden change in light, or a rapid displacement of water can trigger escape responses. But the manta ray's approach does not fit these patterns. It is too slow, too diffuse, too integrated into the environment to be immediately classified as danger. As the manta glides closer, its presence becomes more defined, but still ambiguous. Its large triangular fins extend outward like wings, its body maintaining a consistent orientation as it moves through the water. Its mouth, positioned at the front of its body, remains closed, and its cephalic fins, which can be unfurled to guide water into the mouth, are held in a relaxed position. In this state, the manta appears almost passive, a drifting organism carried by currents rather than an active participant in the ecosystem. This perception is reinforced by the manta's feeding strategy. Unlike many large marine animals that actively pursue prey, the manta ray feeds on plankton, filtering vast quantities of water to extract microscopic organisms. This mode of feeding does not require rapid chases or aggressive strikes. Instead, it involves positioning within areas of high plankton density and moving through them in a way that maximizes intake. However, this apparent passivity conceals a more dynamic behavior that emerges when conditions are optimal. When the manta encounters a dense patch of plankton, often concentrated by currents or upwellings, it can shift from gliding to active feeding with surprising speed. The cephalic fins unfurl, forming a funnel that directs water into the open mouth. The manta accelerates slightly, increasing the flow of water and plankton across its gill rakers, specialized structures that filter out food particles. This transition from passive gliding to active feeding is subtle but significant. The manta does not lunge in the way a predator does, but the change in movement and posture can still be sudden enough to disrupt the immediate environment. Small fish that have been drifting beneath the manta's shadow may find themselves caught in the flow of water being drawn into its mouth. While the manta does not target these fish specifically, they can become incidental prey, swept along with the plankton and consumed. The distinction between intentional predation and incidental capture blurs in this context. The manta ray is not a predator in the traditional sense, yet its feeding behavior can still result in the capture of small organisms that are unable to escape the sudden increase in water flow. This creates a unique interaction where the illusion of harmlessness allows the manta to approach closely, and the mechanics of its feeding then create a localized event of consumption. The ecological implications of this behavior extend beyond individual interactions. By feeding on plankton, manta rays play a role in regulating the distribution and abundance of these foundational organisms. Their movement through the water column can influence the structure of plankton communities, which in turn affects the species that depend on them. In this way, the manta ray contributes to the broader dynamics of the ecosystem, linking microscopic processes to larger-scale patterns. The sensory systems of the manta ray support its ability to navigate and exploit this environment. Its large eyes provide a wide field of vision, allowing it to detect changes in light and movement. Its lateral line system senses vibrations and water flow, helping it to locate areas of higher plankton density. Additionally, manta rays possess electroreceptive capabilities, enabling them to detect the weak electrical signals produced by other organisms. While this sense is more commonly associated with predation in other species, in manta rays, it may contribute to the detection of environmental cues that indicate feeding opportunities. The interplay between the manta ray's size and its behavior is central to its strategy. Its large body could make it an obvious target for predators when it is young, and even as an adult, it must remain aware of potential threats such as large sharks. Yet its slow, controlled movement and the diffuse nature of its shadow reduce the likelihood of detection. It does not attempt to hide its size. Instead, it presents that size in a way that is difficult to interpret, turning what could be a liability into an advantage. As the manta continues its movement through the water, it may encounter other individuals, forming loose aggregations in areas where plankton is abundant. In some cases, these aggregations can lead to coordinated feeding behaviors, where multiple manta rays move in patterns that concentrate plankton and increase feeding efficiency. These interactions add another layer to the ecological role of the species, demonstrating a capacity for behavior that is both individual and collective. The environment itself responds to these movements. Plankton distributions shift, small fish adjust their positions, and the patterns of light and shadow continue to evolve as the sun moves across the sky. The manta ray remains a part of this dynamic system, its presence influencing and being influenced by the conditions around it. As the light begins to fade and the water takes on deeper hues, the shadow of the manta becomes less distinct, blending even more seamlessly into the surrounding darkness. Its movements remain steady, its form continuing to glide through the water with minimal disturbance. In this lower light, the illusion of harmlessness is even more pronounced, as the boundaries between objects become less defined. In the end, the manta ray's strategy is not about deception in the aggressive sense, but about misinterpretation. It does not mimic another organism or actively disguise itself. Instead, it exists within the natural variability of the environment, presenting a form and movement that do not immediately trigger recognition as a threat. This allows it to move freely through open water, approaching feeding opportunities without causing alarm. Through the use of shadow, scale, and motion, the manta ray demonstrates that even in the most exposed environments where there is seemingly nowhere to hide, survival can be achieved by altering perception. It is not always necessary to disappear. Sometimes it is enough to be seen, but not understood, to pass through the field of view as something familiar, something harmless, until the moment when the true nature of the interaction becomes clear.